Look up at the night sky. You see those countless points of light, the familiar shapes of constellations, the moon hanging in its silent orbit. We look at this cosmic vista and we feel like we know it, don't we? We've seen it in countless movies, read about it in books, absorbed these ideas about the universe since we were children. But here's a question that might just stop you in your tracks. How much of what you think you know about space is actually true? What if the most dramatic, exciting, and seemingly solid facts you've learned are actually complete fabrications, misunderstandings, or science fiction fantasies that have been masquerading as truth for decades? It's a strange feeling, realizing that the universe you thought you understood might be entirely different, that the reality is far more bizarre, more complex, and honestly, more incredible than the myths we've been telling ourselves. That's the journey we're embarking on together today. We are about to shatter 30 of the most widespread and stubborn myths about our cosmos. We're talking about everything from the terrifying nature of black holes and the boiling blood of astronauts to the real story behind the dark side of the moon and the truth about little green men. These aren't just minor errors, these are ideas that have become embedded in our culture, repeated in classrooms, and shown in blockbuster films, creating a popular version of space that is often completely at odds with the hard, beautiful, and sometimes unsettling facts uncovered by scientists. So get ready to have your mind completely rewired. This isn't about memorizing dry facts, it's about rediscovering the universe. We're going to peel back the layers of fiction and reveal the stunning scientific truths hiding beneath. It's a journey of discovery that will change the way you see that starry sky forever, replacing old myths with a sense of genuine wonder for what's really out there. And so we begin with one of the most persistent and proudly shared facts in the world, a statement you've likely heard your entire life, that the Great Wall of China is the only human-made structure visible from space. It's a captivating idea, isn't it? A testament to human achievement so immense that it can be seen from the void itself. But the moment we bring science into the picture, this grand claim completely unravels. Let's talk about the view from low Earth orbit where the International Space Station flies. From that altitude, about 250 miles up, the Earth is a vast, breathtaking panorama. Astronauts report that continents, weather systems, and the deep blue of the oceans dominate the view, but seeing the Great Wall, it turns out to be incredibly difficult, and for one fundamental reason: human visual acuity. From that distance, the wall is simply too narrow. It's only about 30 feet wide on average, roughly the width of a country road. To the naked eye from orbit, that thin line blends in perfectly with the colors and textures of the surrounding landscape, its stones and earth materials making it virtually indistinguishable from the mountains and ridges it traverses. It's not a matter of it being faint, it's a matter of it being below the resolution of human sight at that scale. But what about the atmosphere itself? Even on a perfectly clear day, our planet's blanket of air acts as a veil. Atmospheric haze, dust, and pollution scatter sunlight, reducing contrast and making low-contrast, narrow features like the wall even harder to pick out. This isn't just a theoretical problem. It's been confirmed by the very people who have been there. Astronauts from the early days of the space program to those living on the space station today have consistently reported that without powerful camera lenses or binoculars, they simply cannot see the Great Wall with their own eyes. The Chinese astronaut Yang Liwei, the first person China sent into space, explicitly stated he could not see the Great Wall, dealing a major blow to this national myth within China itself. The legendary astronaut Chris Hadfield has also spoken about this, explaining that from orbit, the wall is just too narrow and follows the natural topography, making it camouflage itself against the land. So if the Great Wall is effectively invisible to the unaided eye, what can we see? The real champions of human visibility from space are not narrow stone walls, but light. Vast, sprawling cities illuminated at night create brilliant, unmistakable patterns. The bright glow of Las Vegas or the northeastern seaboard of the United States are far more distinct and recognizable from orbit than any single structure during the day. Even large-scale daytime features like major airport runways, desert irrigation circles, or the massive green and brown geometric patterns of farmland are more readily apparent. The truth is, the myth likely gained traction because of early, grainy satellite photographs where interpreters thought they could identify the wall. But those images were taken with powerful cameras, not the human eye. The reality of space is a lesson in perspective. It shows us that our grandest earthly creations are, on a planetary scale, incredibly delicate. The idea that a single wall could dominate the view from space is a human-centered fantasy. The cosmos gives us a humbler and in many ways more beautiful truth that from the grand vantage point of orbit, it is the collective glow of our civilization, not our individual monuments, that truly marks our presence on the pale blue dot we call home. But speaking of being invisible from space, that brings us to another celestial body that plays a constant game of hide and seek with us here on Earth, our own moon. And with it, one of the most deeply ingrained misconceptions of all. We've all heard the term, popularized by music and mystery, the dark side of the moon. It conjures images of a place of perpetual, chilling blackness, a hidden hemisphere forever shrouded in shadow, untouched by the sun's warm rays. It sounds like the perfect setting for a science fiction thriller. The only problem is it's a complete misnomer. The reality is far more interesting and reveals a fundamental quirk of cosmic mechanics. The confusion comes down to a simple but crucial distinction: the difference between the dark side and the far side. The so-called dark side isn't actually dark at all. It's simply the far side, the half of the moon that is permanently turned away from the Earth. And the reason for this is a beautiful, elegant phenomenon known as tidal locking. Think of it like this. Imagine you're walking in a circle around a friend, but you always keep your face pointed toward them. You're still moving in a full circle, and you're still experiencing a full day and night as you move. But from your friend's perspective, they only ever see your front. They never see your back. That's essentially what the moon does with Earth. Billions of years of Earth's gravitational pull have acted like a gentle brake, slowing the moon's rotation until it became perfectly synchronized with its orbit. The moon takes about 27 days to complete one rotation on its axis, and it also takes about 27 days to complete one orbit around Earth. This one-to-one spin-orbit resonance means that from our vantage point, we are forever destined to see only one face of our celestial companion. Now, because the moon is a sphere orbiting the sun, every single part of its surface, from the familiar craters of the near side to the mysterious highlands of the far side, experiences sunlight and darkness in a regular cycle. A day on the moon from one sunrise to the next lasts about 29.5 Earth days. That means for roughly 2 weeks, the entire far side of the moon is bathed in brilliant, unfiltered sunlight. Then it experiences 2 weeks of night. It gets just as much sun as the side we see. There's nothing inherently dark about it. We have overwhelming proof of this from spacecraft. Every single mission that has ever orbited the moon, from the Apollo command modules to modern orbiters like NASA, a lunar reconnaissance orbiter, has flown around the back and taken stunning, sunlit pictures of the far side. The very first human eyes to see it directly were those of the Apollo 8 astronauts in 1968, when their spacecraft swung around from behind the moon and they were stunned to see a rugged, crater-pocked landscape illuminated by the sun. So why does this myth persist so stubbornly? It's likely because we simply can't see it. The far side is mysterious because it is hidden from our direct view, not because it is devoid of light. Its invisibility sparks our imagination, and the phrase dark side is just so poetically compelling that it has stuck in our culture, even though it's scientifically inaccurate. The true nature of the moon's rotation gives us a profound lesson in orbital dynamics. It shows us that the cosmos is full of these subtle gravitational dances, where bodies become locked in a celestial embrace, revealing only one face to their partners for eternity. That hidden hemisphere isn't a land of eternal shadow. It's a fully sun-washed world in its own right, a testament to the fact that sometimes what we call dark is simply that which we cannot directly see. Moving from the silent, airless moon to the sun itself, we encounter a myth so fundamental to our language and our perception that it almost feels wrong to question it. We look up at the sun and we describe it in the most primal human terms. It is a ball of fire. We feel its heat on our skin. We see its brilliant, flickering light, and our brains, wired by millennia of experience, instantly categorize it alongside a campfire or a blazing torch. But this intuitive connection is a cosmic illusion. The reality of what the sun is and how it generates such staggering amounts of energy is far more powerful, more bizarre, and more magnificent than mere burning. To understand why, we need to draw a critical distinction between two completely different physical processes: chemical combustion and nuclear fusion. The fire we are familiar with here on Earth is a chemical reaction. It requires three things: a fuel like wood or gasoline, an oxidizer, which is almost always the oxygen in our atmosphere, and a source of heat to get it started. When you light a match, the heat breaks the chemical bonds in the wood and the surrounding oxygen, and they rapidly rearrange themselves into new molecules, primarily carbon dioxide and water vapor. This rearrangement releases energy in the form of heat and light. It's a process happening at the atomic level where atoms trade partners, but the atoms themselves, the cores of the carbon, oxygen, and hydrogen, remain completely unchanged. They are just dancing with different partners. Now, let's journey into the heart of the sun. The conditions there are almost unimaginable. The core is a cosmic pressure cooker, with temperatures soaring to over 15 million degrees Celsius and pressures millions of times greater than the atmosphere at Earth's surface. Under these extreme conditions, something entirely different happens. The process isn't chemical, it's nuclear. The fuel isn't wood or gas, but the simplest element in the universe: hydrogen. At the sun's core, the hydrogen is so hot and so compressed that the individual hydrogen atoms are stripped of their electrons, creating a seething plasma of bare atomic nuclei called protons. In this chaotic soup, these protons are moving at incredible speeds. Occasionally, and this is the key part, they collide with such immense force that they overcome their natural electromagnetic repulsion. The same force that makes two positive ends of a magnet push away from each other. When they get close enough, an even more powerful but much shorter range force takes over, the strong nuclear force. This force glues the protons together. This is nuclear fusion. In a multi-step process that is the sun's primary engine, 4 hydrogen nuclei are fused together to create one nucleus of a new, heavier element, helium. But here's the truly mind-bending part. If you add up the mass of 4 individual protons and compare it to the mass of the resulting helium nucleus, you'll find that the helium nucleus is just a little bit lighter. A tiny fraction of the original mass has simply vanished. Where did it go? This is where Albert Einstein's most famous equation, E=mc², comes into play. That missing mass hasn't disappeared. It has been converted directly into a colossal amount of pure energy. The m is the tiny amount of mass lost, and the c is the speed of light, a number so enormous that when you square it, it means even a minuscule amount of mass transforms into an unbelievable explosive force. Every single second, the sun fuses approximately 600 million tons of hydrogen into 596 million tons of helium. The missing 4 million tons of mass is converted directly into energy, the energy that warms our planet, fuels life, and has lit up the solar system for the last 4.5 billion years. This isn't a chemical burn, it's a continuous universe-shaping hydrogen bomb contained and regulated by the sun's own immense gravity. So why does the sun look like fire? The light and heat we receive are the final products of this incredible nuclear chain reaction, born in the core. That energy takes thousands of years to travel outward through the dense layers of the sun, finally bursting from the surface we see, the photosphere, as a brilliant, turbulent glow. The flickering, roiling appearance that reminds us of flame is actually the churning of this superheated plasma at the surface. It's the visible signature of the maelstrom beneath, not the calm oxidation of a log in a fireplace. Grasping this distinction doesn't diminish the sun's majesty, it elevates it. We are not warmed by a distant bonfire, but by the radiant echo of a nuclear furnace that recycles the very fabric of matter itself into the light that allows us to see and the energy that allows us to live. And this brings us to one of the most visually iconic and yet most misunderstood experiences of spaceflight, the idea of zero gravity. We've all seen the videos astronauts floating effortlessly through their spacecraft, tools drifting in mid-air, a stray blob of water shimmering as it hangs in the cabin. It's an image so powerful that it has given rise to the common phrase zero gravity or zero G. It seems to suggest that astronauts have traveled so far from Earth that they have left its gravitational pull behind, entering a true gravity-free void. This picture, however, is an illusion. The reality is not only more fascinating but also a perfect demonstration of one of the most elegant principles of physics. The truth is, gravity is everywhere. It is the fundamental force that holds the universe together, governing the motion of planets, stars, and galaxies. There is no magical boundary you cross where gravity simply stops. In fact, at the altitude where the International Space Station orbits, about 250 miles above the Earth's surface, the force of gravity is still remarkably strong. If you could build a tower that high and stand on top of it, you would weigh only about 10% less than you do on the ground. So why do the astronauts float? The secret isn't the absence of gravity, it's the nature of their motion. They are quite literally falling. To understand this, let's do a simple thought experiment. Imagine you are standing on the edge of a very high cliff and you throw a baseball perfectly horizontally. The ball will follow a curved path as it falls, arcing down to hit the ground some distance away. Now throw it harder. It will travel farther before it curves down to the ground. Now, imagine you had a cannon that could launch a projectile with such incredible speed that its forward motion perfectly matches the rate at which it falls. As the cannonball falls toward the Earth's surface curves away beneath it at exactly the same rate. The cannonball is in a perpetual state of falling, but it never gets any closer to the ground. This is precisely what an orbit is. It is a controlled, continuous fall around the planet. This state of continuous freefall creates the sensation we call weightlessness. The astronauts and their spacecraft are both falling together, accelerating toward Earth at the same rate. Since everything is falling in sync, there is no force pushing the astronauts against the floor or the walls. They experience this as a complete lack of the sensation of weight. Scientists more accurately call this environment microgravity, a term that highlights the presence of minuscule, residual forces while acknowledging that the dominant experience is one of apparent weightlessness. It's a subtle but crucial distinction. They haven't escaped gravity, they are mastered by it, using its pull to whip around the planet at over 17,000 miles per hour. You can even experience a tiny taste of this right here on Earth. Think about when you're in a fast-moving elevator that begins to descend rapidly. For a brief moment, as the elevator car accelerates downward, you feel a little lighter, as if you're floating slightly in your shoes. That's because the floor is dropping away from your feet at the same rate you are falling. In a roller coaster, as it crests a hill and plunges downward, you feel that same lifting sensation in your stomach, a moment of weightlessness. The astronauts on the space station are simply in that same state of freefall, but their incredible horizontal speed ensures they keep missing the Earth, turning a terrifying plunge into a stable, endless orbit. So the next time you see that breathtaking footage of life aboard the station, remember, you're not looking at an environment without gravity. You are witnessing a sublime, perpetual dance with gravity, a perfect balance between falling and flying that allows humanity to live and work in the sky. We just explored the elegant physics of orbit, revealing that the sensation of weightlessness is really a state of continuous freefall. This principle governs not just our spacecraft, but every single body in our solar system, from the tiniest asteroid to the largest planet. And when we apply that same lens of relentless physics to the worlds orbiting our sun, we stumble upon one of the most counterintuitive facts in all of astronomy. If I were to ask you which planet holds the title for the hottest in our solar system, your logical guess might be the one closest to the sun. It seems straightforward, right? The closer you are to the fire, the hotter you get. This is the common sense reasoning that makes the myth that Mercury is our solar system's hottest planet so pervasive. But the cosmos often delights in defying our common sense, and this is a perfect example. The reality is a tale of two worlds and the profound importance of having or not having a shirt. Let's start with Mercury. As the innermost planet, it is indeed subjected to the full, blistering intensity of the sun. At its equator during the long Mercurian day, surface temperatures can skyrocket to a searing 800 degrees Fahrenheit. That's certainly hot enough to fry electronics and make any human visit a very short, very catastrophic affair. But here's the critical detail that changes everything. Mercury is a barren, airless rock. It's essentially a planetary cinder, possessing only the faintest wisp of an exosphere, nowhere near thick enough to be called a true atmosphere. Think of Mercury like a car parked in the desert sun with all its windows rolled down. The metal of the door might get painfully hot to the touch, but the inside of the car isn't trapping that heat. The moment the sun sets, that heat radiates away almost instantly into the void of space. And on Mercury, where a single day lasts 59 Earth days, the sunset brings a truly dramatic change. Without a blanket of air to hold onto the warmth, the surface temperature plummets. The same ground that was at 800 degrees can plunge to nearly negative 300 degrees Fahrenheit by the middle of the long night. It's one of the most extreme temperature swings in the entire solar system, all because Mercury has no atmosphere to act as a thermal regulator. Now let's travel outward to the second planet from the Sun, Venus. At first glance, this shouldn't be the winner. It orbits almost twice as far from the Sun as Mercury does. It receives only about a quarter of the solar energy per square meter that Mercury endures. By that logic alone, it should be significantly cooler. But Venus plays by a completely different set of rules, and it holds a secret that makes it the undisputed, terrifying champion of heat. Venus is shrouded in an incredibly thick, permanent blanket of clouds. This isn't just a few puffy cumulus clouds. This is a global, suffocating atmosphere composed almost entirely of carbon dioxide, with clouds of sulfuric acid swirling within it. The atmospheric pressure at the surface of Venus is 92 times greater than the pressure we experience at sea level on Earth. It's the equivalent of being nearly 3,000 feet underwater. This dense, heavy atmosphere is the key to Venus's hellish nature. What happens on Venus is a textbook example, in fact, the textbook example of a runaway greenhouse effect. Here's how it works. Sunlight, in the form of visible light, passes through Venus's thick clouds and reaches the surface. The ground absorbs this energy, and as all warm things do, it re-radiates it back outward as infrared radiation, which we feel as heat. On Earth, a good portion of this infrared radiation escapes back into space, keeping our planet's temperature in a comfortable balance. But on Venus, that dense carbon dioxide atmosphere acts like a one-way door. The CO2 molecules are exceptionally good at absorbing this outgoing infrared radiation. They trap the heat, preventing it from escaping, and then re-radiate it in all directions, including back toward the surface. This creates a relentless, self-perpetuating cycle. More heat gets trapped, which heats the surface and the lower atmosphere even more, which in turn radiates even more infrared energy, which gets trapped again. The planet essentially bakes itself from the inside out. The result of this planetary pressure cooker is almost beyond comprehension. The average surface temperature on Venus is a constant 867 degrees Fahrenheit. That's not a daytime high, that's the average day and night at the poles and at the equator. It is hotter than the surface of Mercury at its absolute peak, and it stays that way all the time. This temperature is hot enough to melt lead, to warp metal, and to instantly destroy any spacecraft humanity has ever sent there within a matter of hours. The Soviet Venera landers, which briefly touched down on Venus in the 1970s and 80s, transmitted back images of a stark, hellish landscape before being crushed and melted by the immense pressure and heat. Visualize the two planets side by side. Mercury, a sun-scorched, cratered world with wild temperature swings, looking much like our moon. Then picture Venus, a deceptively beautiful, bright white pearl in our sky, hiding a surface that is a literal inferno, with temperatures so uniform and so extreme that they redefine our understanding of planetary environments. So the myth that Mercury is the hottest planet is a powerful reminder that proximity isn't everything. It's a lesson in the delicate balances that govern a world's climate. Mercury, for all its proximity to the Sun, is a simple rock, heating and cooling with the stark simplicity of physics in a vacuum. Venus, on the other hand, shows us the terrifying power of an atmosphere gone wrong. It stands as a stark warning, a nearby example of how a greenhouse effect, when pushed to its extreme, can transform a world that might have once been Earth-like into the hottest, most hostile place in our entire solar system. From the hellish, pressurized oven of Venus, our journey through cosmic misconceptions now takes us outward, into the great expanse between Mars and Jupiter. This is the realm of the asteroid belt, a place that has been utterly transformed in our collective imagination by the dramatic demands of science fiction. Think of those classic space adventure films where the heroic starship is suddenly confronted by a chaotic, deadly field of tumbling space rocks. The pilot grips the controls, swerving violently left and right, while alarms blare and massive boulders spin menacingly close, shattering against the hull. It's a thrilling, white-knuckle sequence that paints the asteroid belt as an impossibly dense, chaotic, and impassable cosmic minefield. This cinematic trope is so powerful that it feels intuitively true. But when we compare it to the reality, as revealed by the unblinking eyes of our robotic explorers, the truth is almost laughably different. The asteroid belt is not a navigational nightmare. In reality, it is overwhelmingly, profoundly empty. To understand why, we need to grasp the sheer, mind-boggling scale of our solar system. The main asteroid belt is not a narrow ring, it's a vast, donut-shaped region orbiting the Sun. Its inner edge begins roughly 220 million miles from the Sun, and it stretches outward to about 330 million miles. That's an enormous band of space, hundreds of millions of miles across. Now, let's populate this vast volume. Within it, we have discovered over 1 million asteroids, with many more smaller ones likely waiting to be found. That sounds like a lot, and it is, until you distribute them across the immensity of the belt. If you could take every single known asteroid and lump them all together into one single, solid object, its total mass would be less than that of our own moon. All that rock and metal scattered across a cosmic highway that dwarfs the entire space between Earth and the Sun. This leads to the most critical statistic that debunks the myth. The average distance between any two significant asteroids in the belt is about 1 million miles. Let that number sink in for a moment. 1 million miles, that is more than 4 times the distance from the Earth to the Moon. Imagine you are a spacecraft pilot and your nearest rocky neighbor is 1,000,000 miles away. You are not weaving through a dense obstacle course. You are sailing through a cosmic ocean so empty that you would be extraordinarily lucky to even see a single asteroid as a discernible disk out your window during your entire voyage through the belt. The probability of a random, unintentional collision with a large asteroid is astronomically low, so low that mission planners for interplanetary probes don't even factor it into their risk calculations. They don't need to plot a careful, zigzagging path. They simply aim for their destination, flying in an almost perfectly straight line, with a near certainty that they will never come close to anything substantial. We have direct visual proof of this from the very missions that have traveled through this region. Consider the Voyager probes, which in the late 1970s and 80s shot through the asteroid belt on their way to the outer planets. Their cameras captured nothing but the starry blackness of space. There were no frantic maneuvers, no close calls. They sailed through as if it were any other part of the solar system, because for all practical purposes it was. Decades later, the Dawn spacecraft performed an even more incredible feat. It didn't just pass through the belt, it took up residence there, becoming the first mission to orbit two different celestial bodies, the protoplanets Vesta and Ceres. The stunning images and data Dawn sent back revolutionized our understanding of these ancient worlds, but the most profound lesson from its journey was the emptiness it encountered between them. To reach Vesta and then later Ceres, Dawn traveled for years across millions of miles of virtual nothingness, its path a serene and uneventful arc through the so-called crowded belt. So why does the myth of an impassable belt persist with such tenacity? It's a classic case of artistic license. A realistic depiction of a spacecraft flying through the asteroid belt would be, from a filmmaker's perspective, incredibly boring. You would see a star field and maybe, after years of travel, a distant, faint point of light that slowly grows into a world. There is no drama, no immediate peril. To create tension and visual excitement, directors compress the scale, bringing the asteroids impossibly close together to create a thrilling sequence of near misses. This powerful imagery, repeated in film after film, has overwritten the scientific reality in our minds. The true nature of the asteroid belt is not one of chaotic danger, but of silent, majestic isolation. It's a relic of the early solar system, a collection of building blocks that never formed a planet, forever separated by distances so vast they humble our human sense of scale. Navigating it isn't a test of evasive piloting. It's a testament to our ability to calculate precise orbits across millions of miles of emptiness, aiming not to avoid rocks, but to find the rare, fascinating worlds hidden within the void. The universe has a way of presenting us with concepts so alien and powerful that they seem to defy all logic, and perhaps no other object in the cosmos has been more misunderstood and more sensationalized than the black hole. We picture them as monstrous, all-consuming entities, cosmic vacuum cleaners roaming the galaxy, sucking in everything in their path with an unstoppable, infinite hunger. It's a terrifying image born from a misunderstanding of their true nature. The reality is far more nuanced, and it hinges on a simple but profound principle. A black hole's gravitational pull is not a magical suction force. It's governed by the same rules of gravity that keep your feet on the ground and the Earth in orbit around the Sun. Let's break this down with a thought experiment that might just change your entire perspective. Imagine we could magically and instantly replace our Sun with a black hole of exactly the same mass. What would happen to the Earth? The dramatic Hollywood answer would be our planet being violently ripped from its orbit and spiraling inward to its doom. But the scientific answer is surprisingly calm, and it reveals everything. Our Earth would continue to orbit this new, dark central point in exactly the same path at the same speed for the same billions of years it was already destined to. The seasons would continue to cycle, the year would remain the same length. The only thing that would change catastrophically for us is the light and the heat. We would be plunged into an eternal, deep freeze because the light and warmth that sustain our world would be gone, but gravitationally, nothing would change. The force holding us in our cosmic dance depends only on the mass of the central object and our distance from it. Whether that mass is in the form of a brilliant, fusion-powered star or an infinitely dense, dark singularity, the gravitational effect on our orbit is identical. This reveals the core truth about black holes. They aren't gravitational outliers, they are gravitational concentrators. The black hole part isn't what has the gravity, the mass has the gravity. The terrifying power of a black hole comes not from having more gravity than a star, but from packing all that stellar gravity into an incomprehensibly tiny point, allowing you to get unnervingly, dangerously close to an enormous amount of mass. With a normal star like our Sun, you can only get so close before you physically hit its fiery surface, about 432,000 miles away from its center. But a black hole of the same mass has no physical surface. Its mass is concentrated in a point of infinite density called a singularity, and around that point lies the boundary of no return, the event horizon. This is the key to understanding the real danger. Think of the event horizon not as a physical membrane, but as a point of no return threshold in space itself. It's the ultimate one-way door. The gravitational pull at the event horizon is so strong that the escape velocity, the speed you would need to achieve to break free, equals the speed of light. Since nothing in the universe can travel faster than light, nothing that crosses this boundary, not even light itself, can ever come back out. This is the true nature of the danger. It's not that a black hole reaches out and grabs you from afar with some special force. It's that if you wander too close, if your path takes you across that invisible mathematical line, then you are irrevocably lost. Outside the event horizon, the physics is familiar. You could, in theory, orbit a black hole just as you would a star, provided you maintained a safe distance. A black hole doesn't suck. Its gravity attracts just like any other object. The difference is the consequence of getting too close. With a star, getting too close means you burn up. With a black hole, getting too close means you cross a threshold from which the universe itself offers no escape. This distinction completely reframes our understanding. A black hole isn't an active predator hunting for matter. It's more like a perfectly camouflaged, bottomless well in the fabric of space-time. If you stay away from the edge, you can walk around it safely. But if you misstep and fall in, there's no climbing back out. This is why the image of a black hole as a roaming vacuum cleaner is a myth. In the vast emptiness of space, simply being near a black hole is no more dangerous than being near a star of the same mass. The peril only manifests at the most extreme proximity, a lesson in cosmic boundaries that transforms the black hole from a mindless devourer into a fascinating and ultimately lawful manifestation of gravity pushed to its absolute limit. The universe has a beginning. It's a statement that feels both profound and unsettling, and for generations, the name we've given to that beginning has painted a very specific and ultimately misleading picture in our mind. We call it the Big Bang. The words themselves suggest a violent, chaotic, explosive event, a cosmic bomb detonating at a single point in an empty, pre-existing void, flinging matter outward into the darkness. It's a powerful and intuitive image, but it is perhaps the single greatest misnomer in all of science. The reality is far stranger and requires us to fundamentally redefine what we mean by the word space and beginning. The Big Bang was not an explosion in space, it was the rapid initial expansion of space itself. To grasp this crucial distinction, we need to let go of the idea of a central point of origin. An explosion, like a grenade or a firework, happens at a specific location within a pre-existing space. Shrapnel flies outward from the center into the surrounding area. The Big Bang was nothing like that. Instead of something exploding into space, space itself began to expand, carrying the nascent universe with it. A helpful, though imperfect, way to visualize this is the classic balloon analogy. Imagine the surface of a partially inflated balloon. Take a marker and place several dots all across its surface. These dots represent galaxies. Now slowly inflate the balloon. Watch what happens to the dots. Each dot grows steadily farther away from every other dot. There is no central dot that is the center of the expansion. From the perspective of any single dot, all the other dots are moving away. The space on the surface of the balloon is what is stretching, carrying the dots apart. This is a two-dimensional analogy for our three-dimensional space. In our universe, it is the fabric of the cosmos itself that is stretching, causing galaxies to recede from one another. This leads directly to one of the most monumental discoveries in the history of astronomy. In the 1920s, the astronomer Edwin Hubble was studying the light from distant galaxies and made a startling observation. With very few exceptions, nearly every galaxy he could see had its light shifted toward the red end of the spectrum. This redshift is a telltale sign that an object is moving away from us, much like the sound of a receding ambulance siren drops in pitch. The truly revolutionary part was this: the farther away a galaxy was, the greater its redshift. The most distant galaxies were fleeing the fastest. This wasn't a random scattering of motions. It was a clean, mathematical relationship showing that the entire universe is systematically expanding. If you could run the film of the cosmos backward, you would see all those galaxies converging, not to a single point in space, but to a state where all of space was incredibly dense and hot. The Big Bang marks the moment that expansion began. But if this theory is correct, there should be a relic, a faint echo of that primordial state, still permeating the entire cosmos. And in the 1960s, two radio astronomers named Arno Penzias and Robert Wilson accidentally found it. They were working with a large, sensitive radio antenna and were plagued by a persistent, faint static that came from every direction in the sky. They assumed it was some kind of equipment fault or perhaps interference from pigeon droppings, but after eliminating every possible source, the hum remained. They had inadvertently discovered the cosmic microwave background, or CMB. This is the cooled and stretched remnant of the first light that ever traveled freely through the universe. In the earliest moments, the universe was so hot and dense that it was an opaque plasma, a soup of particles and energy where light couldn't travel far before bouncing off an electron. But about 380,000 years after the Big Bang, the universe had expanded and cooled enough for atoms to form. Suddenly, light could travel unimpeded. That first flash of light, once blazingly bright and energetic, has been traveling for over 13 billion years. The expansion of the universe itself has stretched its wavelengths, cooling it down from visible light into the microwave part of the spectrum, leaving it as a uniform glow that fills every cubic inch of the cosmos with a temperature just a few degrees above absolute zero. The static on an old-fashioned analog television, about 1% of that snow, is literally the afterglow of the Big Bang, the oldest light in the universe arriving at your screen. So when we speak of the Big Bang, we are not talking about an event that happened somewhere out there. It happened everywhere. The space that you are occupying right now was once part of that incredibly dense, hot state. Every location in our current universe was, in a very real sense, at the center of that initial expansion, because the expansion created the very concept of where. This reframes our entire understanding of the cosmos. We are not living in the aftermath of a debris field flying away from a long-ago explosion. We are living within the expanding fabric of reality itself, riding a wave that began from a state of such extreme physics that our current laws cannot even describe it. The Big Bang wasn't an explosion in the void. It was the moment the void itself began to be. Our journey through cosmic myths now brings us to one of the most visceral and terrifying ideas put forward by science fiction: the fate of an unprotected human in the vacuum of space. The cinematic image is dramatic and gruesome. An astronaut suit ruptures, and their body instantly swells and violently explodes into a cloud of frozen gore. It's a shocking visual that plays on our deepest fears, but it is a profound exaggeration. The reality of exposure to vacuum is certainly lethal, but its mechanics are far more clinical and biologically strange than a simple explosion. The primary and most immediate danger isn't your body bursting, but your brain shutting down. From the moment you are exposed to the vacuum, the clock starts ticking with brutal efficiency. You have about 10 to 15 seconds of useful consciousness. Why so fast? It's not that the air is violently sucked from your lungs. It's that there is essentially zero oxygen pressure to push life-sustaining molecules into your bloodstream. Your body's existing oxygen, no longer being replenished, is rapidly depleted. The carbon dioxide in your blood begins to drop precipitously as well, which might sound like a good thing, but it's not. This sudden drop triggers an automatic reflex, causing the blood vessels in your brain to constrict. This protective mechanism, meant to preserve oxygen, instead leads almost instantly to hypoxia, a severe oxygen shortage in the brain. You don't have time to panic or feel your body swell. You simply lose consciousness. It's a swift, silent knockout. Now, what about that famous idea of your blood boiling? This is where the physics gets particularly counterintuitive. Here on Earth, we think of boiling as a process driven by heat. You apply thermal energy to a liquid until it turns to vapor. But in the vacuum of space, boiling is a function of pressure or the lack thereof. Every liquid has a vapor pressure, a point at which it will spontaneously turn into a gas. At sea level on Earth, the air pressure is high enough to keep your bodily fluids in a liquid state. But in space, where the pressure is effectively zero, the boiling point of water and other fluids drops to below your body's internal temperature. This means the fluids on the surface of your body, the saliva on your tongue, the tears in your eyes, the moisture in your lungs, would indeed begin to vaporize. You wouldn't feel a searing heat, but a strange, evaporative cooling as the most energetic molecules escape as vapor. This is known as ebulism. Crucially, however, your circulatory system is a closed, pressurized network. Your skin and the walls of your blood vessels are remarkably strong and elastic, maintaining enough internal pressure to prevent your blood from boiling inside your veins and arteries. The pressure within your cardiovascular system is sufficient to keep your blood in a liquid state for a time. So, while the moisture in your lungs and on your mucous membranes would vaporize, your blood does not begin to bubble and froth throughout your body. The human body is resilient enough to contain itself, at least for a short period. We are not relying solely on theory here. Tragic accidents and controlled experiments have given us a grim but clear picture. In 1966, a technician at NASA was inside a vacuum chamber testing a spacesuit when a hose came disconnected, suddenly exposing him to a near-perfect vacuum. He lost consciousness in just 12 to 15 seconds. Fortunately, the chamber was repressurized within a minute, and he regained consciousness almost immediately. He later reported that the last thing he remembered was the sensation of the saliva boiling on his tongue. This real-world incident aligns perfectly with our scientific understanding. Animal experiments conducted in the 1950s and 60s also demonstrated that subjects could survive exposures of up to 90 seconds if repressurized in time, with the most immediate and irreversible damage being brain death from oxygen deprivation, not physical disintegration. The real, long-term cause of death in an unrecovered exposure would be the combination of that rapid brain hypoxia and the damage to your lungs and soft tissues from ebulism. Your lungs, filled with vaporizing moisture, would suffer trauma, and the entire experience would lead to fatal swelling and circulatory collapse, but over a timescale of 1 to 2 minutes, not instantly. The myth of the explosive death is a dramatic oversimplification. It ignores the body's own structural integrity and the precise, sequential way in which biology fails in the absence of pressure. The true horror of space exposure isn't a cinematic burst, but a silent, swift loss of consciousness followed by a systemic biological collapse, a quiet, clinical end that is, in its own way, just as terrifying as the fiction. It's a story that just won't go away, whispered in online forums and presented in grainy documentaries as the ultimate government cover-up. The Apollo moon landings were an elaborate hoax staged on a film set to win the Cold War. It's a compelling narrative for those who distrust authority, but when you actually examine the evidence, not the supposed anomalies, but the positive, physical, and independently verifiable proof, the conspiracy theory completely disintegrates under the weight of overwhelming fact. Let's start with one of the most elegant and undeniable pieces of evidence, something you can't fake with Hollywood special effects, a simple mirror. During the Apollo 11, 14, and 15 missions, the astronauts left behind arrays of small, corner cube mirrors called retroreflectors on the lunar surface. These are not ordinary mirrors. They are designed with exceptional precision to reflect light directly back to its source, no matter the angle it arrives from. For over 5 decades, observatories on Earth have been firing powerful laser pulses at these exact locations on the moon. The beam travels the 240,000 miles to the moon, bounces off the retroreflector left there by human hands, and a tiny, predictable fraction of that light makes the return journey to be detected by telescopes on Earth. By precisely timing this round trip, which takes about 2.5 seconds, scientists can calculate the distance to the moon with an accuracy of a few millimeters. This ongoing experiment, known as lunar laser ranging, has provided crucial data for testing Einstein's theory of relativity and studying the moon's orbit. You cannot fake a physical object that is still actively being used for precise scientific measurement 250,000 miles away. Then consider the sheer scale of the alleged deception. The Apollo program wasn't a small, secret project. It employed over 400,000 people, engineers, scientists, technicians, programmers, and factory workers across the entire United States. Are we to believe that not a single one of these individuals over the course of a decade has ever come forward with a single piece of incontrovertible physical evidence of the hoax? That every last person involved maintained this perfect, lifelong silence? The conspiracy would have to be orders of magnitude more complex and perfectly executed than the moon landing itself. We have thousands of hours of mission audio, hundreds of thousands of photographs, and reels of film, all documenting every step of the process from design to splashdown. Conspiracy theorists often point to a handful of these photos, claiming anomalies like strange shadows or a missing field of stars. But each of these has a straightforward explanation grounded in the unique environment of the lunar surface. The shadows aren't parallel because they are cast on a rolling, uneven terrain under a single, distant light source, the sun. The sky is black and starless because the lunar surface is brightly lit by the sun, and the camera exposures were set for daylight, making the faint stars invisible, just as you can't see stars from a brightly lit city street. These aren't evidence of a hoax, they are evidence of a real place with different physical conditions than Earth. Perhaps the most compelling geopolitical argument, however, comes from America's greatest rival. The Soviet Union was in a fierce, desperate space race with the United States. They had their own robust space program with a vast network of tracking stations, spy satellites, and intelligence agents dedicated to monitoring every American move. They had every motivation in the world to expose a fake moon landing. It would have been the propaganda coup of the century, humiliating the United States on the global stage. And they had the technical capability to do so. They were tracking the Apollo spacecraft with their own powerful radars. Yet, at no point did the Soviet government or its scientific community ever claim the landings were fake. They formally congratulated NASA on the success of Apollo 11 and entered into discussions for the collaborative Apollo-Soyuz mission just a few years later. Their silence is a deafening testament to the reality of the achievement. They knew it was real because their own instruments confirmed that American astronauts were traveling to the moon and back. The idea that the greatest technological accomplishment of the 20th century was a fraud is not just a misunderstanding of science and photography. It's an insult to the ingenuity, the courage, and the sheer hard work of the thousands of people who made the impossible happen. The evidence isn't just on the ground or in the photo archives. It's etched into the history of the Cold War itself, verified by the very people who had the most to gain by calling it a lie. Stargazers and navigators have looked to the heavens for millennia, and among the countless points of light, one star has held a place of unique prominence in human history. We call it the North Star, Polaris, and its reputation is so legendary that a common assumption has taken root. It must be the brightest, most brilliant star in the entire night sky. Why else would it be so special? This belief seems logical, but it's a perfect example of how cultural importance can be mistaken for physical supremacy. The truth is, Polaris is not the brightest star in our sky. In fact, it doesn't even crack the top 40. Its fame comes not from its luminosity, but from its incredibly fortunate location, a celestial anchoring point that has guided travelers for centuries. To understand this properly, we need to talk about how astronomers measure a star's brightness using a system known as apparent magnitude. This scale is a little counterintuitive because the brighter the object, the lower its magnitude number. The planet Venus, for instance, can shine at a brilliant magnitude of -4. Sirius, the actual brightest star in our night sky, blazes at an apparent magnitude of -1.46. It's a dazzling jewel in the constellation Canis Major, outshining everything else. Now, where does our famed North Star sit on this scale? Polaris has an apparent magnitude of around 1.98. That makes it a reasonably bright star, easily visible to the naked eye, but it's utterly outclassed by several others. Consider Canopus, the second brightest star, glowing in the southern sky with a magnitude of -0.74. Or even Alpha Centauri, the closest star system to our own, which appears as a single, very bright point to our eyes. If you were to line them up in the sky, Sirius would appear nearly 25 times brighter than Polaris. The North Star is a steady, reliable lantern, but it is far from the most powerful beacon in the cosmic darkness. So, if it's not the brightest, why has Polaris been so crucial to human civilization? The answer lies in a beautiful coincidence of geometry. Our planet spins on a tilted axis, and if you were to extend that imaginary axis line from the North Pole directly out into space, it would point almost perfectly to Polaris. This means that as Earth rotates throughout the night, every other star appears to wheel in great circles around the sky, but Polaris remains nearly stationary, fixed directly above the North Celestial Pole. For anyone in the Northern Hemisphere, its height above the horizon corresponds directly to your latitude. This made it an indispensable tool for navigation. Sailors, explorers, and desert travelers could always find true north by locating Polaris, providing a constant, unwavering reference in a turning sky. Its value was in its position, a fixed point in the cosmic clockwork, not in its raw power. It's the stellar equivalent of a lighthouse keeper who never leaves his post. He might not be the loudest or most flamboyant person on the coast, but his steadfast presence is what makes him indispensable. This distinction helps us appreciate the true diversity of the cosmos. The brightness of a star as seen from Earth depends on two primary factors: its intrinsic luminosity, how much energy it actually puts out, and its distance from us. Sirius is so bright partly because it is intrinsically more luminous than our Sun, but also because it is relatively close to us, a mere 8.6 light-years away. Polaris, on the other hand, is a remote supergiant star located about 430 light-years from Earth. It's actually a profoundly powerful star, but its immense distance dims its light to a modest gleam in our sky. Recognizing this allows us to see the night sky not as a flat canvas, but as a three-dimensional volume where a star's apparent significance is a complex interplay of its true nature and its location in the vastness of space. The myth of Polaris's supreme brightness is a reminder to look deeper, to understand that sometimes the most important guide is not the one that shouts the loudest, but the one that holds its ground with unwavering consistency. But for a phenomenon that feels so intimately tied to the moon, it turns out our planet's daily rise and fall of water is a celestial tug of war with two powerful players. The idea that the tides are caused only by the moon is a classic half-truth. While our lunar companion is the dominant force, it's not acting alone. The sun, despite being almost 400 times farther away, is so incredibly massive that its gravitational pull also has a profound, undeniable effect on our oceans. Understanding how these two gravitational giants work together, and sometimes against each other, reveals the beautiful complexity behind the rhythm of the seas. To grasp this, we need to revisit the fundamental mechanism of tides. It's not simply the moon pulling upward on the water. The key is the difference in gravitational pull across the Earth. The side of Earth facing the moon feels a stronger gravitational tug than the center of the planet, and the center feels a stronger pull than the side facing away. This difference stretches the entire Earth, but since the solid ground is rigid, the effect is most visibly apparent in the fluid, mobile oceans. This creates two tidal bulges, one on the side closest to the moon and another, surprisingly, on the exact opposite side. Imagine gently stretching a water balloon. It bulges at both ends. As the Earth rotates daily beneath these two bulges, any given coastline will experience two high tides and two low tides in a roughly 25-hour cycle. The moon's gravity is the primary architect of this basic pattern. Now, bring the sun into the picture. Our star exerts its own tidal force on the Earth, and while it's only about 46% as strong as the moon's, it acts as a powerful modulator. The sun's influence doesn't create its own separate pair of bulges. Instead, it deforms the lunar bulges, either amplifying them or diminishing them. This is where the concepts of spring tides and neap tides come into play, and they are all about the geometry of the sun, Earth, and moon. Twice a month, during the full moon and the new moon, the three bodies line up in a straight line. In this syzygy alignment, the gravitational pulls of the sun and moon are working in concert, pulling in the same direction. Think of it as two people on opposite ends of a rope, both pulling in sync. This combined force tugs the ocean bulges even higher and pulls the low tides even lower. The result is the spring tide, which has nothing to do with the season, but comes from the Old English word springen, meaning to rise up. These are the most dramatic tides of the month, with the greatest difference between high and low water, often leading to spectacularly high water levels on coastlines. Conversely, twice a month during the first and third quarter moons, the sun and moon are at a right angle relative to the Earth. From our perspective, the moon appears half-lit. In this configuration, the sun's gravitational pull is working against the moon's, essentially pulling at cross purposes. The sun's force tries to create its own bulges at a 90-degree angle to the moon's, which has the effect of flattening the primary lunar bulges. It's like our two people on the rope are now pulling at right angles to each other, cancelling out some of the overall stretch. This creates the neap tide, from the Old English nep, meaning scant or lacking. During neap tides, the difference between high and low water is at its minimum. The high tides are noticeably less high and the low tides are less low, creating a much more subdued tidal range. This constant gravitational dance between our two primary celestial neighbors means the tides we experience are never just the moon's doing. They are a dynamic, ever-changing sum of two separate gravitational influences. The moon sets the fundamental beat, the daily rhythm of two highs and two lows, but the sun acts as the conductor, controlling the volume of that rhythm. making it swell into a powerful spring tide crescendo or fade into a gentle neap tide lull every 2 weeks. It's a perfect demonstration that even in the vastness of space, forces interact in a predictable mathematical ballet, and by understanding this interplay, we can read the story of the solar system written in the daily pulse of our own shores. Next time you see a picture of a comet streaking across the sky with its long, brilliant tail streaming behind it, what description comes to mind? We often call it a blazing comet, a fiery streak, language that paints a picture of an object burning up as it screams through the void. It's a powerful, almost primal image, but it's a complete mischaracterization of what a comet actually is and what its magnificent tail represents. The truth is, there is no fire involved, no combustion whatsoever. A comet is not a cosmic cinder, it is a cosmic iceberg, and its tail is not a trail of smoke and flame, but a ghostly, sun-lit banner of ice and dust. To understand this, we need to look at the fundamental nature of a comet itself. Astronomers often affectionately call them dirty snowballs, or more accurately, icy dirt balls. This simple term captures their essence perfectly. Imagine a massive, mountain-sized conglomerate of primordial ice, rock, and frozen gases, water ice, carbon dioxide, ammonia, and methane, all mixed together with ancient, dark dust and organic compounds. This is the comet nucleus, the solid heart of the object. For most of its long, elliptical orbit, a comet is just this dormant, frozen nucleus, a dark and inert chunk sailing through the outer darkness of the solar system. The magic and the source of the spectacular display only begins when it approaches the warmth of the sun. As a comet's orbit carries it inward, solar heating begins to vaporize the ices on or near its surface. This process is called sublimation, where solid ice turns directly into gas, skipping the liquid phase entirely. This is not burning. It's the same process that makes a cube of dry ice disappear into a cold fog here on Earth. The escaping gases erupt from the nucleus, pulling along with them countless tiny dust particles that were trapped within the ice. This creates a vast, tenuous cloud around the nucleus called the coma, which can be hundreds of thousands of miles across. The coma is what gives the comet its fuzzy, glowing head. But the most iconic part, the magnificent tail, is created by two relentless forces emanating from the sun, sunlight and the solar wind. This is where the story gets truly beautiful, because a comet doesn't just have one tail. It typically has two distinct tails created by different mechanisms and pointing in slightly different directions. First, there is the dust tail. This is formed by the microscopic dust particles liberated from the nucleus. The pressure of the sunlight itself, a physical force called radiation pressure, pushes these small particles away from the comet's head. Because this pressure acts continuously, the dust tail often appears broad, softly curved, and brilliantly white or yellowish. It shines simply by reflecting sunlight, much like a cloud in the sky reflects the light of the day. It's a trail of the comet's own substance, a slow, graceful arc of primordial dust being gently blown by the photon breeze from the sun. The second tail is often more dramatic and structured, the ion tail, also known as the plasma tail. This one is born from the solar wind, a constant supersonic stream of charged particles, protons and electrons blasting outward from the sun. The ultraviolet light from the sun is so energetic that it knocks electrons right off the gas molecules in the coma, a process called ionization. This creates a plasma of charged particles. The magnetic field carried by the solar wind then sweeps up these ions, accelerating them and carrying them directly away from the sun. The ion tail, often glowing with a distinctive blue hue, is always pointed directly away from the sun, regardless of the comet's direction of travel. It's straighter and more structured than the dust tail because it's locked in a magnetic embrace with the solar wind. The beautiful glow comes from the ions themselves, which get excited and then release light at specific wavelengths as they calm down, a process similar to what happens in a neon sign. We no longer have to rely on distant observations from Earth to confirm this. our robotic emissaries have given us an intimate look right into the heart of a comet. The European Space Agency's Rosetta mission performed one of the most incredible feats in space exploration by not just flying by a comet, but by actually orbiting comet 67P Churyumov-Gerasimenko for 2 years and deploying a lander onto its surface. The images and data it sent back are nothing short of revolutionary. They showed us the comet's nucleus in stunning detail, a bizarre, duck-shaped world of stark cliffs, deep pits, and rolling plains, all made of black, porous ice and dust. Rosetta witnessed the comet's activity wake up as it approached the sun, watching jets of gas and dust erupt from its surface like geysers. It analyzed the composition of the coma, directly confirming the presence of water vapor, carbon monoxide, and a cocktail of other molecules. Most importantly, it showed us the tails forming not from fire, but from this sublime interaction between icy vapor and solar radiation. The mission painted a portrait of a comet not as a destructive ball of fire, but as a fragile, active, and ancient world, a pristine relic from the solar system's birth that puts on one of the most beautiful and misunderstood light shows in the cosmos. So the next time you witness a comet gracing our skies, remember you are not looking at a burning arrow. You are seeing a cosmic sculptor at work, where the invisible tools of sunlight and solar wind carve a magnificent, ephemeral masterpiece from a simple, dirty snowball. This idea that the universe must have a central point, a place where it all began, feels like it should be the most basic question of cosmology. Where is the center of everything? Yet, this seemingly simple inquiry leads us to one of the most profound and counterintuitive truths in all of science. The universe does not have a center. There is no privileged location, no cosmic point zero from which everything is flying away. To understand why, we need to let go of our earth-bound intuition and embrace a much grander, more mind-bending perspective on what the expansion of the universe actually means. Let's return to that powerful balloon analogy, which gives us a tangible way to visualize this. Picture the universe not as the empty space inside the balloon, but as the entire two-dimensional surface of the balloon itself. Now take a marker and draw many dots all over this surface. Each dot represents a galaxy. As you slowly inflate the balloon, watch what happens. Every single dot begins to move away from every other dot. From the perspective of any dot you choose, all the other dots are receding. There is no dot on that stretching surface that is the center of the expansion. The center of the expansion, in this analogy, is the third-dimensional point in the very middle of the balloon, a point that is not part of the two-dimensional universe on the surface. For the dots living in their two-dimensional world, that central point doesn't even exist. Their entire reality is the expanding surface they inhabit. This is a powerful, albeit simplified, model for our own three-dimensional universe. The expansion isn't happening within a pre-existing space, it is the expansion of space itself. There is no central point in our three-dimensional universe because every location is part of the stretching fabric. This leads directly to the revolutionary observational evidence that cemented our modern understanding, the redshift of distant galaxies. When astronomers like Edwin Hubble pointed their telescopes at other galaxies, they found that the light from almost all of them was shifted toward the red end of the spectrum. This redshift is a cosmic speedometer, indicating that these galaxies are moving away from us. The truly groundbreaking discovery was the pattern. The farther away a galaxy is, the faster it appears to be receding. This relationship, known as Hubble's law, is exactly what you would expect if the very space between galaxies was stretching. Imagine our balloon again, with dots spaced at different intervals. As the balloon inflates, the distance between two dots that were already far apart will increase by a larger amount per second than the distance between two dots that were close together. From any single dot's viewpoint, the more distant dots appear to be fleeing faster. This is precisely what we see from our vantage point on Earth. It's not that we are at some special center of a cosmic explosion. It's that in an uniformly expanding universe, every observer on every galaxy would see the exact same thing, all other galaxies moving away with the most distant ones speeding off the fastest. This brings us to the ultimate logical conclusion about the Big Bang. If every point in space is moving away from every other point, then running the cosmic film backward in time forces all of those points to converge. But they don't converge to a single location in space. They converge to a state where all of space was infinitely, or near infinitely dense and hot. The Big Bang, therefore, did not happen at a point in the universe. It happened to the entire universe everywhere at once. The space that you are sitting in right now, the space between your eyes and this screen, was once part of that incredibly dense, hot state. From our perspective, it certainly looks like we are at the center of the expansion because we see all galaxies rushing away from us. But an alien astronomer on a planet in the Andromeda galaxy would make the exact same observation. From their telescope, they would see the Milky Way along with every other galaxy rushing away from them. Every location in the cosmos can rightly claim to be the center from its own point of view because the expansion has no single origin point within the fabric of space-time. The center is everywhere and it is nowhere, a concept that challenges our very perception of reality, but is supported by the relentless, consistent data written in the light of the receding cosmos. This particular myth taps into a deep-seated, almost primal fear, the idea of an unseen, unstoppable world lurking in the outer darkness, on a predetermined path to collide with our own and wipe the slate clean. The story of Planet X, or Nibiru, is a sprawling saga that blends fringe astronomy, misinterpreted ancient texts, and outright fiction into a potent doomsday cocktail. Its origins are often traced back to the writings of Zecharia Sitchin in the 1970s, who claimed to have translated ancient Sumerian tablets that described a rogue planet called Nibiru with a long, elliptical orbit that brought it through the inner solar system every 3,600 years. According to this narrative, this planet was home to an advanced alien race, the Anunnaki, who genetically engineered humanity. The modern doomsday twist emerged when various pseudoscientific groups and internet theorists took this idea and combined it with a misreading of the Maya calendar, predicting a cataclysmic encounter for the year 2012. When that year came and went without incident, the date was simply shifted forward, a classic tactic of doomsday prophets that allows the myth to persist indefinitely, always just beyond the horizon of disproof. The scientific case against the existence of such a planet, however, is not based on shifting dates, but on the immutable and all-seeing laws of physics, specifically gravity. In our solar system, every single massive body, from the Sun to the smallest asteroid, exerts a gravitational pull on every other body. The orbits of the planets we know are not just random paths, they are precise, predictable solutions to a complex gravitational dance. If a planet large enough to be called Nibiru, often described as a super-Earth or even a brown dwarf, were anywhere in our solar system, especially on an orbit that brought it anywhere near the inner planets, its gravitational influence would be unmistakable. It would be like having an unseen elephant in a room. You might not see it, but you would certainly notice the floorboards bending, the furniture shaking, and the other occupants being pulled toward it. Astronomers would observe pronounced, unexplained wobbles in the orbits of all the other planets, particularly the outer gas giants. We can track the positions of these worlds with incredible precision, and their paths match the predictions of our gravitational models that include only the known planets, asteroids, and comets. There is no gravitational kick or tug left unaccounted for that would hint at a massive hidden perturber. The math simply doesn't lie. The dance floor of the solar system is not crowded with an uninvited, monstrous guest. But what about the vast, unexplored reaches beyond Neptune, in the cold, dark domain of the Kuiper Belt? Could a planet be hiding out there, too distant and too faint for our telescopes to see? This is where modern, all-sky surveys have completely closed the door on the possibility. The most powerful evidence comes from NAS, a Wide-Field Infrared Survey Explorer, or WISE telescope. This remarkable instrument scanned the entire sky in infrared light, which is perfect for detecting the faint heat signature of large, cool objects that would be nearly invisible in optical light. If a planet the size of Neptune or larger existed within 10,000 times the Earth-Sun distance, WISE would have spotted it. If something as massive as Saturn were lurking in the outer solar system, it would have been easily visible. The WISE mission and its subsequent analysis as the NEOWISE project has comprehensively mapped the celestial neighborhood. The results are definitive. No unknown object of significant size exists within the region where a planet X on a doomsday orbit could possibly hide. The data shows no signs of a giant planet, often nicknamed Planet 9, in legitimate astronomical searches for a much smaller, distant perturber of Kuiper belt objects, which is a separate scientific hypothesis and in no way related to the destructive Nibiru of doomsday lore. This brings us to the final, most logical nail in the coffin for this myth: orbital dynamics. The kind of orbit described for Nibiru, a highly elliptical path that regularly plunges through the densely packed inner solar system, is one of the most unstable configurations imaginable. A planet on such a trajectory would have its orbit drastically altered by the gravitational slingshot effects of the giant planets, especially Jupiter, during its first few passes billions of years ago. It would either be ejected from the solar system entirely, flung into the sun, or its orbit would be circularized into a stable path. There is no mechanism by which such a chaotic, death-dealing orbit could be maintained over thousands of cycles as the myth claims. The solar system is a stable, well-ordered system that has settled into its current configuration over 4.5 billion years. A massive, disruptive world on a collision course with Earth would be the single most obvious gravitational and thermal signature in the entire sky to our instruments. The enduring power of the Nibiru myth isn't a testament to its scientific validity, but to a powerful human psychology that is sometimes drawn to narratives of impending catastrophe. It's a story that thrives in the gaps of our knowledge, but as those gaps have been systematically filled by missions like WISE, the room for this fictional planet has vanished entirely. We can look to the skies with confidence, knowing that our cosmic neighborhood is mapped, measured, and reassuringly free of hidden doomsday worlds. Leaving behind the phantom threat of Nibiru, we arrive at a myth born not from doomsday prophecies, but from a single, grainy photograph that captured the world's imagination and ignited a firestorm of speculation. In 1976, NAS, a Viking 1 orbiter, was methodically mapping the Martian surface when its cameras captured an image of a region called Cydonia. The picture revealed what appeared to be a colossal, human-like face staring up from the rusty plains, complete with distinct eyes, a nose, and a mouth. It was an image so striking, so seemingly deliberate, that it sparked a cultural phenomenon. Here, at last, was the evidence so many had been waiting for, proof of a lost Martian civilization, a monument left by intelligent beings, a sphinx of another world. For decades, this face on Mars became a cornerstone of extraterrestrial conspiracy theories, a symbol of what NASA was supposedly hiding from the public. The only problem is, when we finally got a better look, the face completely vanished, revealing a truth that is just as fascinating, but for entirely different reasons. The real story of the face is a testament to the power of improved technology and perspective. The original Viking image had a resolution of about 150 feet per pixel. At that level of detail, a complex geological formation, when viewed from directly overhead under the specific lighting conditions of a Martian afternoon, could indeed cast shadows that resembled facial features. It was a perfect storm of low-resolution, oblique sunlight and the human mind's incredible capacity for pattern recognition. But science doesn't settle for a single, blurry snapshot. Decades later, a new generation of orbiters arrived at Mars, equipped with cameras of breathtaking power. Missions like NASA Mars Global Surveyor and the European Space Agency's Mars Express aimed their high-resolution instruments at Cydonia, capturing images with a clarity the Viking team could only have dreamed of. The results were definitive. The face was revealed to be what geologists call a mesa, a flat-topped hill, much like those found in the American Southwest, heavily eroded by billions of years of Martian winds. The new images showed a rugged, entirely natural landscape of rock and sand, with craters, avalanche chutes, and talus slopes. The symmetrical eyes were simply pits and shadows in the crumbling rock. The nose was a central ridgeline. The illusion of a carved monument was shattered, replaced by the reality of a fascinating but completely natural geological feature. So why did we see a face so clearly in the first place? The answer lies not on Mars, but within our own brains. We are hardwired for a psychological phenomenon known as pareidolia. This is the innate tendency to perceive a familiar pattern, most commonly a face where none actually exists. It's a survival mechanism for our ancestors on the African savanna. Quickly spotting the face of a predator hiding in the bushes or recognizing a friend's expression from a distance was a matter of life and death. Our brains became hyper-efficient facial recognition machines, so good at the job that they often find faces even when they aren't there. We see the scowling visage of the man in the moon, a smiling face in the front of a car, or the figure of the Virgin Mary on a piece of toast. In every case, our brain is taking ambiguous visual information and, in a fraction of a second, fitting it to a pre-existing template. It's a cognitive shortcut that usually serves us well, but in the realm of interpreting alien landscapes from a great distance, it can lead us dramatically astray. The face on Mars is arguably the most famous cosmic example of pareidolia, a celestial Rorschach test that says more about the observer than the observed. This powerful tendency doesn't just explain the face, it helps us understand the entire genre of Martian anomalies that have followed. Proponents of ancient Martian civilizations didn't just see a face, they went on to identify pyramids nearby, fortified cities, and even alien skeletons in later rover images. Each of these, upon closer inspection with better data, has been revealed as a rock formation, a jumble of boulders, or another trick of light and shadow. The process is always the same. A low-resolution image creates ambiguity, and the human brain, craving meaning and narrative, fills in the blanks with the most exciting story it can conceive. The scientific process, in contrast, is a tool designed to counteract this very bias. It demands repeatable observations, higher resolution data, and the constant questioning of initial impressions. The journey from the mysterious Viking photo to the crisp, detailed maps we have today is a perfect illustration of this process in action. It's a story of how curiosity, when paired with rigorous investigation, can replace a compelling fiction with a more complex and in many ways more satisfying truth about the natural world. The real wonder of Cydonia is not a vanished alien monument, but the powerful reminder it offers about our own perception and the incredible, wind-sculpted beauty of a planet that needs no artificial mysteries to be utterly captivating. Think of the most spectacular cosmic event you've ever seen in a movie: a star exploding in a blinding supernova, a starship erupting into a million pieces, two galaxies colliding in a silent, stately dance. In our minds, these events are accompanied by a thunderous, visceral soundtrack. We hear the deep, rumbling roar of the detonation, the sharp, metallic screech of tearing hulls, the percussive blast of expanding shockwaves. This auditory experience is so deeply woven into our expectations that it feels fundamentally true. But the reality of the cosmos presents us with a profound and unsettling truth. In the void of space, no one can hear you scream, or anything else for that matter. The grandest, most violent events in the universe occur in absolute, perfect silence. This deafening quiet stems from a fundamental principle of physics. Sound, as we understand it, is not some ethereal substance that exists on its own. It is a mechanical wave, a physical disturbance that must travel through a medium. Think of it like a wave moving across a pond. The water is the medium. Without it, there can be no wave. Here on Earth, that medium is our atmosphere, a thick soup of nitrogen, oxygen, and other gases. When a guitar string vibrates or your vocal cords tremble, they push and pull on the surrounding air molecules. These molecules then bump into their neighbors, transmitting the energy of that vibration in a chain reaction that eventually reaches your eardrum. Your brain interprets this patterned vibration as sound. Now imagine taking away the air. In the near-perfect vacuum of space, there are simply not enough molecules to bump into each other. There is no medium to carry the vibration. An exploding star releases an unimaginable amount of energy, creating powerful shock waves that propagate through the sparse interstellar gas. But these are not sound waves as we know them. They can heat material and accelerate particles, but they cannot create the rhythmic compression and rarefaction of a medium that our ears would register as a bang, a boom, or a whisper. The explosion would be a brilliant, violent, and completely silent flash of light. This leads to a fascinating contradiction between science and science fiction. Film directors are, of course, masters of emotion and engagement. They know that showing a massive spaceship blowing up in utter silence would feel bizarre, anticlimactic, and emotionally distant to an audience. We are visual creatures, but we are also deeply auditory. A soundtrack gives weight, impact, and emotional resonance to what we are seeing. The roaring engines of the Millennium Falcon, the iconic whine of a lightsaber, the thunderous report of a starship's laser cannons. These are all artistic choices designed to pull us into the narrative, to make the unreal feel tangible and immediate. They are a concession to our earth-bound perception, a necessary lie that makes the fiction feel more real. If a filmmaker were to portray space battles with realistic audio, the only sounds you would hear would be those conducted through the structure of the ships themselves, the muffled clangs and vibrations transmitted through the hull, the sound of the crew's own breathing and voices inside their pressurized cabins. The vast external carnage would play out against a backdrop of nothingness, a disconnect that, while scientifically accurate, would strip the scene of much of its dramatic power. Yet, scientists have found a clever way to listen to the cosmos, albeit not in the way we typically imagine. While there are no traditional sound waves traveling through the void, space is filled with plasma, a hot, charged gas of ions and electrons. This plasma can support the propagation of various types of waves, including electromagnetic waves and plasma waves. Instruments on board spacecraft like NASA Van Allen probes or the European Space Agency's cluster mission are equipped with sensors that can detect the oscillations of these plasma waves. The data they collect is a series of numbers representing frequency and amplitude. Researchers can then take this data and, through a process called sonification, translate it into a form that human ears can perceive. They might scale the frequencies down from inaudibly high ranges to something within our hearing, or assign different values to different pitches. The result is a series of haunting chirps, whistles, whooshes, and rumbles that we often call the sounds of space. These are not sounds that were traveling through space waiting to be heard. They are data-driven audio representations, much like a graph turned into a song. They are an incredibly valuable tool, allowing researchers to identify patterns and phenomena, like the interaction of solar wind with Earth's magnetic field, that might be less obvious in a visual plot. So, while you can't hear a black hole consuming a star, scientists can sonify the ripples it creates in space-time, giving us a powerful, albeit artificial, window into the music of the spheres. This stark divide between Hollywood's thrilling symphony and the universe's profound silence forces us to recalibrate our senses. It teaches us that the cosmos operates on a set of physical rules that are often stranger and more austere than our imaginations. The true grandeur of a supernova isn't diminished by its silence. If anything, its majestic, light-only display becomes even more awe-inspiring when we realize it's a spectacle for the eyes alone. A violent birth or death announced across the light years without uttering a single sound. It seems like one of the most logical connections we can make. As Earth journeys around the Sun, its path isn't a perfect circle, so surely when we're closer, we get summer, and when we're farther away, we get winter. This intuitive idea feels so right, but it contains a fundamental flaw that, once you see it, completely reshapes your understanding of our planet's relationship with its star. The truth is, the changing distance between Earth and the Sun plays a negligible role in creating our seasons. In a stunning twist of cosmic irony, Earth is actually at its closest point to the Sun, a position called perihelion, in early January, right in the middle of the Northern Hemisphere's winter. The real driver of the seasons, the force behind the cycle of frost and bloom, is something far more elegant: the persistent, steady tilt of the Earth's axis. To truly visualize this, you need to picture our world not as a spinning top standing straight up, but as a top that's leaning over. Chinese letter, 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 Chinese letter. Imagine a line running through the Earth from the North Pole to the South Pole. This is our planet's axis. Now, this axis isn't perpendicular to the plane of our orbit around the Sun. Instead, it's tilted away from the vertical by about 23.5 degrees. This is not a temporary posture, it's a constant year-round lean. As Earth makes its year-long journey around the Sun, this tilt remains pointed in the same direction in space, roughly toward the North Star Polaris. This means that for half the year, the Northern Hemisphere is angled toward the Sun, and for the other half, it's tilted away. The Southern Hemisphere experiences the exact opposite pattern. This simple, constant tilt is the master switch for the seasons, and it all comes down to the angle at which sunlight strikes different parts of the globe. Think about shining a flashlight directly onto a table. The light creates a small, intense, bright circle. Now, tilt that flashlight so it hits the table at a shallow angle. The same amount of light is now spread out over a much larger, elongated, and dimmer oval. This is precisely what happens with sunlight on Earth. During the Northern Hemisphere's summer, around June, the North Pole is tilted toward the Sun. Sunlight strikes the northern half of the planet more directly. The energy is concentrated, delivering more heat per square mile. The days are also significantly longer, giving the ground more time to absorb that concentrated energy. Meanwhile, in the Southern Hemisphere, the sunlight is striking at a much shallower angle. The same amount of solar energy is diffused over a wider area, making it less effective at heating the surface. The days are shorter, providing less time for warming. This is why when it's a blazing summer in New York, it's the heart of winter in Sydney. Now, let's return to that surprising fact about distance. Earth's orbit is indeed slightly elliptical, not a perfect circle. The difference between our closest approach, perihelion, and our farthest point, aphelion, is about 3 million miles. While that sounds like a vast gap in the grand scale of our solar system, it's a relatively small variation, changing the total amount of solar energy reaching Earth by only about 7%. This minor fluctuation is completely overwhelmed by the dramatic effect of the axial tilt. The concentration of sunlight due to the direct angle of incidence in summer has a far greater impact on temperatures than this tiny change in distance. The proof is in the timing. Earth is closest to the Sun around January 3rd during the cold of the northern winter, and farthest away around July 4th during the peak of the northern summer. If distance were the primary factor, the entire planet would experience the same season at the same time, and July would be our coldest month, not our warmest. The fact that the hemispheres have opposite seasons simultaneously is the ultimate evidence that the tilt, not the distance, is in command. This elegant celestial mechanism explains so much more than just temperature. It dictates the length of our days, the height of the sun in the sky at noon, and the very character of the weather patterns that define different times of the year. It's a global system of energy distribution that has governed the rhythms of life on our planet for billions of years. Understanding this transforms the seasons from a simple matter of proximity into a dynamic dance of geometry and light, a constant, graceful wobble that brings the cycle of renewal to every corner of the globe. Now that we've unraveled the true cause of our seasons, let's turn our attention to the stars themselves and a deceptively simple assumption about their fiery nature. We look up and we see a tapestry of different colors: a brilliant white Sirius, a noticeably red Antares, the steady yellow glow of our own sun. It feels natural to assume that a red star is burning the hottest, like the embers of a cosmic forge, while a white or blue star must be cooler. But in the realm of stellar physics, our everyday intuition is turned completely on its head. The widespread idea that a star's color is a straightforward indicator of its temperature is actually a half-truth that hides a much more precise and fascinating classification system. The reality is that a star's color is indeed a direct thermometer for its surface temperature, but the relationship is inverted from what you might expect. The hottest stars blaze with a blue-white light, and the coolest stars glow with a deep, somber red. To understand this surprising reversal, we need to think about how objects emit light based on their heat. Imagine a piece of iron being heated in a forge. At first, it doesn't glow at all, it just gets hot. As its temperature rises, it begins to emit a dull, red glow. Heat it further, and that red glow brightens and shifts to orange, then to a brilliant yellow-white, and if you could heat it enough, it would eventually emit a blue-white light. The same fundamental principle of physics, known as black body radiation, applies to stars. A star is essentially a massive, self-luminous ball of plasma, and the color of the light it emits most intensely is a direct consequence of its surface temperature. A cooler object's photons have lower energy, which corresponds to longer wavelengths on the red end of the spectrum. As an object gets hotter, the photons it emits have more energy, shifting the peak of its radiation to shorter wavelengths, first to yellow, then to white, and finally to blue. So, a red star is the cosmic equivalent of a celestial cooling ember, while a blue star is a searing, youthful inferno. This understanding led astronomers to develop a powerful and memorable classification system to catalogue the vast diversity of stars. It's known as the spectral sequence, and its classes are neatly summarized by the mnemonic, "Oh, be a fine guy/girl, kiss me." Each letter represents a major category, running from the hottest to the coolest: O, B, A, F, G, K, M. Our own sun, with its surface temperature of about 5,500 degrees Celsius, is a G-type star, placing it right in the middle of the sequence, a yellow dwarf, a perfectly average star. But to see the extremes of this temperature spectrum, we can look to a single, magnificent constellation, Orion the Hunter. Hanging from Orion's belt is his sword, and there you'll find two magnificent stars that represent the two ends of the stellar temperature scale. First, consider Rigel, the bright star marking Orion's left foot. Rigel is a B-type blue supergiant, a behemoth whose surface temperature soars to a staggering 12,000 degrees Celsius. Its intense heat causes it to radiate most of its energy in the blue and ultraviolet parts of the spectrum, making it shine with a piercing, brilliant blue-white light. It is one of the most luminous stars in our entire galaxy. Now, shift your gaze to the opposite shoulder of the giant, to the star Betelgeuse. This is a classic M-type red supergiant, a star in the final stages of its life. While its core is furiously hot, its surface has expanded to a truly monstrous size, becoming diffuse and cool. The surface temperature of Betelgeuse is a relatively tame 3,300 degrees Celsius. At this lower temperature, its light peaks in the red and infrared wavelengths, giving it its distinctive, warm, orange-red hue to our eyes. It's the difference between the focused, searing flame of a welder's torch and the sprawling, warm glow of a campfire. This comparison within a single constellation beautifully illustrates the entire stellar classification system in one glance. The system goes even deeper, with each major class being subdivided by numbers from 0 to 9. For instance, an A0 star is hotter than an A9 star, which is just a step away from an F0. This creates a smooth, continuous temperature gradient across the heavens, from the blistering O-types at over 30,000 degrees to the cool, faint M-types just a few thousand degrees hot. This color-temperature relationship is more than just a way to sort stars. It's a fundamental tool that allows astronomers to unravel the life stories of these distant suns. A star's color and temperature are directly linked to its mass and its stage in life. Massive, heavyweight stars burn their nuclear fuel at a prodigious rate, achieving tremendous temperatures and shining with a brilliant blue light, but they live fast and die young, exploding as supernova after only a few million years. Lower mass stars like our steady sun are more frugal, burning for billions of years as stable yellow stars before eventually swelling into red giants. The coolest, smallest stars, the red dwarfs, are so efficient that they can shine for trillions of years, far longer than the current age of the universe. So when you learn to read the color of a star, you are not just noting its surface condition. You are reading its birth certificate, its current vital signs, and its ultimate fate. The night sky transforms from a random scattering of points into a detailed census report, where a star's hue tells you everything about its mass, its age, and the furious nuclear processes happening deep within its heart. We have a saying here on Earth, a piece of folk wisdom meant to offer a strange kind of comfort in the middle of a thunderstorm. Lightning never strikes the same place twice. It's an assurance that the worst is over, that the random fury of nature has moved on. But like so many earthly assumptions, this one completely falls apart when we leave our atmosphere and look at the dynamics of other worlds. In the realm of planetary science, this myth is not just false, it's spectacularly inverted. To find the ultimate debunking, we need to travel to the solar system's largest planet, a world where lightning isn't a rare and fleeting event, but a constant planet-wide symphony of electrical fury. Welcome to Jupiter, where lightning doesn't just strike the same place twice, it strikes the same places thousands of times, in storms that have raged for centuries, if not millennia. Our understanding of Jovian lightning has been completely revolutionized by a dedicated robotic explorer, NASA Juno spacecraft. Since it arrived at the gas giant in 2016, Juno has been performing daring close-pass orbits, diving deep into the planet's violent radiation belts to get a closer look than any probe before it. It's equipped with a suite of instruments specifically designed to peel back the layers of Jupiter's atmosphere, and one of its most revealing tools is its microwave radiometer, which can peer deep into the cloud tops, and its onboard cameras and lightning detection systems. The data and images Juno has sent back have painted a picture of a world where lightning is not just common, but a fundamental part of its atmospheric engine. We're not talking about the familiar forked lightning we see on Earth. Much of the activity Juno has detected originates from powerful bolts of shallow lightning and mushball phenomena, where an ammonia water solution acts as an antifreeze, creating slushy hailstones that generate immense electrical charges through collision. These flashes are immense, often containing energies far greater than their terrestrial counterparts. Now consider the most famous feature on Jupiter, the Great Red Spot. This colossal anticyclonic storm is larger than our entire planet and has been churning for at least hundreds of years. Storms on Jupiter aren't measured in hours or days. They are permanent, stable features of the atmosphere, locked in by jet streams that race around the planet at thousands of miles per hour. Within these vast, swirling systems, the conditions for lightning are perpetually met. Juno's instruments have detected countless lightning strikes originating from the deep convective clouds within these giant storm systems, day after day, orbit after orbit. The lightning is striking the same vast, stormy regions over and over and over again. There is no moving on because the storm itself doesn't move on. The atmospheric dynamics that create the lightning are built into the very structure of Jupiter's weather. The planet is a tapestry of these semi-permanent tempests, each one acting as a relentless lightning factory. But the evidence isn't just in the raw data, it's in the stunning visual captures. Juno Cam, the spacecraft's public outreach camera, has provided us with breathtakingly detailed images of Jupiter's polar regions, a place earlier missions like Voyager could barely glimpse. At the poles, we don't see the familiar banded structure of the equator. Instead, we find a chaotic, stunning landscape of swirling cyclones. The North Pole is dominated by a central cyclone surrounded by 8 others, each one as wide as the continental United States. The South Pole features a similar arrangement with 5 of these gargantuan storms. These are not transient weather patterns, they are stable, geometric arrangements of colossal vortices that have remained in place for years. And within each of these polar cyclones, Juno's sensors have detected a constant, flickering dance of lightning. These are places where the electrical discharges are so frequent and repetitive that if you could stand on a hypothetical platform in the middle of one, the sky would be in a near-continuous state of illumination. The concept of lightning avoiding a previous strike location becomes meaningless here. The entire storm cell is the target, and it is being struck relentlessly. So why does this happen? The key lies in the fundamental differences between Earth and Jupiter. Our planet has a solid surface that heats and cools unevenly, driving weather systems that are relatively short-lived and mobile. A thunderstorm forms over a region, dumps its rain and lightning, and then dissipates or moves with the prevailing winds. Jupiter has no solid surface to disrupt the flow. It's a ball of hydrogen and helium all the way down, with atmospheric dynamics driven almost entirely by internal heat left over from its formation. This creates a system of incredibly stable, long-lived jet streams and storm structures. The energy for the lightning comes from the immense upward convection of moist air from the planet's hot interior. As these rising plumes of gas condense and form slushy hail, the charge separation occurs and the lightning flashes. Because the convective engine is constant and the storm structures are locked in place by the jet streams, the lightning simply keeps happening in the same vast atmospheric arenas. It's a self-perpetuating cycle on a scale that dwarfs human comprehension. This transforms the old saying from a comforting platitude into a profound lesson in planetary science. The rule on Earth is a statistical fluke, a consequence of our particular and dynamic weather patterns. On Jupiter, the rule is repetition. The Jovian environment shows us that under the right, or perhaps from our perspective, the terrifyingly wrong, conditions, lightning doesn't just strike the same place twice. It establishes a permanent residence, illuminating the fact that the laws of physics are universal, but the conditions under which they play out can create realities vastly different from our own. The next time you hear that thunderclap, remember that on a world 500 million miles away, the sky is lit by 1,000 similar flashes, each one a testament to the enduring, repetitive power of nature when it operates on a planetary scale. When we contemplate the journey to the moon, our minds often leap to the vast emptiness of space or the perils of landing on an alien surface. But nestled much closer to home, between Earth and the moon, lies a phenomenon that has become the subject of intense speculation and fear: the Van Allen radiation belts. Popular portrayals sometimes cast these belts as an impenetrable, fiery barrier of lethal radiation, a cosmic minefield that should have cooked the Apollo astronauts and that supposedly proves their mission was impossible. The truth, however, is a masterclass in nuance, planning, and the clever application of physics. The Van Allen belts are not a solid wall of death. They are a region of trapped energetic particles that, while hazardous, were a known and managed risk, traversed successfully not just by Apollo, but by hundreds of missions since. To understand how this was possible, we first need to grasp what the Van Allen belts actually are. They are not a uniform soup of radiation filling space. Instead, imagine two gigantic, donut-shaped regions encircling Earth's equator, held in place by our planet's powerful magnetic field. The inner belt is primarily composed of very energetic protons, while the outer belt contains mostly high-energy electrons. These particles, originating from the solar wind and cosmic rays, become trapped, spiraling along the magnetic field lines between the north and south magnetic poles. The belts are dynamic, swelling and shrinking with solar activity, but their structure is predictable. Crucially, they are not a solid, homogeneous shell. Their intensity varies dramatically with both distance from Earth and latitude. The most intense radiation is concentrated around the magnetic equator and drops off significantly as you move toward the magnetic poles. This geographical variation in the belt's density was the key to the Apollo mission strategy. The Apollo spacecraft did not simply punch straight through the heart of the most intense regions. Engineers and trajectory planners used their detailed maps of the belts to chart a course that minimized exposure. The chosen path took the spacecraft through the thinnest, least active parts of the belts, specifically by using a high-inclination orbit that bypassed the most dangerous equatorial zones. Think of it like navigating a mountain range. You wouldn't try to climb the highest, most treacherous peak. You would find the lowest, safest pass to travel through. The Apollo trajectory was that cosmic mountain pass. Furthermore, the transit was remarkably swift. The powerful Saturn V rocket accelerated the spacecraft to escape velocity so quickly that the entire journey through the most concerning portions of the belts took only about an hour. This short exposure time was a critical factor in keeping the radiation dose manageable. Then there was the spacecraft itself. The Apollo command and service modules were not flimsy tin cans. They were designed with radiation in mind. The aluminum hull of the spacecraft provided a significant degree of shielding, enough to drastically reduce the dose from the relatively diffuse radiation encountered in their chosen flight path. The astronauts themselves were also protected by their spacesuits during the transit, which offered additional layers of material. The radiation dose the crew received during their entire journey through the belts was carefully measured with personal dosimeters. The data confirmed what the physicists had predicted. The total dose was in the range of a few millisieverts. To put that in perspective, that's roughly equivalent to the amount of background radiation a person on Earth receives over the course of a few months, or similar to the dose from a couple of medical CT scans. It was a measurable, but by no means lethal, exposure. The crew's total radiation dose for the entire Apollo mission was less than what the International Space Station crew receives over a similar period, as the station, while in a relatively low radiation orbit, is exposed continuously for months, whereas the Apollo passage was a brief, one-time event. We continue to operate in and around the Van Allen belts today with a sophisticated understanding of their nature. Satellites in geostationary orbit, which is within the outer belt, are built with radiation-hardened components to withstand the long-term exposure. The International Space Station orbits well below the bulk of the inner belt in a relatively benign region. Robotic missions to the Moon and beyond routinely pass through the belts without issue, their systems protected by design. The story of the Apollo missions and the Van Allen belts is not one of impossible odds, but one of brilliant engineering and meticulous planning. It showcases humanity's ability to understand a complex natural phenomenon, map its dangers, and then devise an elegant and effective strategy to overcome it. The belts are a hazard to be respected and mitigated, not an impassable barrier. They stand as a testament not to the impossibility of space travel, but to our capacity to solve profound challenges with knowledge, preparation, and courage. For centuries, a deep copper-red moon hanging in the night sky has sent shivers down the spines of people across the globe. It's been seen as a divine portent, a warning of impending doom, the anger of the gods made manifest in the heavens. The term blood moon itself carries this heavy, supernatural weight, evoking images of ancient prophecies and cosmic vengeance. But what if this terrifying celestial spectacle is not a sign from the universe at all, but rather a reflection of our own world, a beautiful and predictable consequence of the simple physics of light and shadow? The truth transforms this omen into one of the most elegant demonstrations of our place in the solar system. The entire phenomenon begins not with the moon, but with a perfect cosmic alignment. A total lunar eclipse occurs when the sun, Earth, and moon line up in a nearly straight line, with Earth positioned directly in the middle. As the moon travels in its orbit, it glides into the long, cone-shaped shadow that our planet casts out into space. This shadow is actually composed of two distinct parts, the lighter outer penumbra and the much darker central umbra. The drama unfolds as the moon first touches the penumbra, then begins its slow, steady journey into the deep umbral shadow. This is the moment of totality, when the entire lunar disk is engulfed by Earth's shadow. But if Earth's shadow is dark, why doesn't the moon just disappear into blackness? This is where the magic happens, and the key is our planet's atmosphere. Imagine our atmosphere as a giant, global, and slightly distorted lens encircling the entire Earth. While the solid body of our planet blocks all direct sunlight from reaching the moon, our atmosphere does not. Sunlight skimming the edges of Earth gets filtered through this blanket of air. And just as it does every evening during a sunset, our atmosphere scatters the shorter, bluer wavelengths of light. This is called Rayleigh scattering, the same effect that makes our daytime sky blue. The blue light gets redirected out in all directions, leaving behind the longer, redder wavelengths to continue on their journey. This filtered crimson light is then bent or refracted by our atmosphere, curving inward enough to softly illuminate the surface of the eclipsed moon. The moon, in essence, is being lit by the combined light of every sunrise and every sunset happening around the entire rim of Earth at that very moment. It's a planetary sunset projected onto a lunar canvas. You can see this same color transformation right here on Earth. Think about the vibrant reds and oranges that paint the sky as the sun dips below the horizon. The sunlight has to travel through a much thicker slice of atmosphere at that low angle, scattering away the blue and green light and allowing the stunning reds to dominate. A lunar eclipse is precisely the same effect, just viewed from a different perspective. Instead of looking at the sunset, you're standing in the shadow it creates and looking back at the object being illuminated by its warm, residual glow. The exact color and brightness of the eclipsed moon can even serve as a crude diagnostic tool for the health of our own planet. If Earth's atmosphere is clear and stable, the moon will often appear a bright coppery orange or even a fiery red. However, if a major volcanic eruption has recently filled the stratosphere with dust and aerosols, the eclipse can be much darker, sometimes making the moon nearly disappear. The most famous example of this followed the massive eruption of Mount Pinatubo in 1991, which led to an exceptionally dark lunar eclipse the following year. So the blood moon is not a sign of a troubled cosmos, it's a subtle report on the current state of our own world's air. This scientific understanding stands in stark contrast to how ancient cultures interpreted this event. For them, without the framework of orbital mechanics, the slow, inexorable dimming and reddening of the moon was a terrifying mystery. The Mayans believed a jaguar was attacking the moon, and they would make as much noise as possible to drive the beast away. The ancient Chinese saw it as a sign that a dragon was consuming the moon, and they too would bang drums and create a cacophony to frighten it into spitting the moon back out. In Mesopotamian cultures, a lunar eclipse was often seen as a direct assault on the king, who was considered a divine representative. To confuse any evil forces, a temporary substitute king would be placed on the throne during the eclipse, only to be quietly disposed of once the danger had passed, ensuring the real king's safety. These stories, while born from fear, highlight a universal human desire to explain and control the seemingly chaotic forces of nature. Our modern knowledge hasn't stripped the total lunar eclipse of its power, it has instead given it a new kind of majesty. We no longer look up in superstitious dread, but in quiet awe. We understand that we are witnessing a celestial ballet of shadow and light, a demonstration that our world is part of a dynamic physical system. We can predict these events with astonishing accuracy, knowing the exact minute when the moon will begin to slip into shadow and the precise hour when it will emerge, glowing once more with reflected sunlight. This predictability is a triumph of human reason, replacing fear with foresight. The blood moon is not an omen of disruption. It is a symbol of cosmic order, a regular reminder that our planet is an active participant in the solar system, casting its own tinted shadow and painting its companion world with the gentle, rosy light of 1,000 simultaneous dawns and dusks. When you picture astronauts preparing for a mission, you might imagine them floating effortlessly inside a giant hangar, a room where gravity has been somehow switched off, allowing them to practice for the weightlessness of space. It's a wonderful image, but the reality of their training is far more ingenious and, frankly, more grueling. Astronauts do not train in actual zero gravity because creating a true, sustained zero-G environment on Earth is, with our current technology, impossible. Instead, they use two brilliant methods that cleverly simulate the sensation and effects of weightlessness, each with its own unique purpose and challenges. The first method delivers short, intense bursts of microgravity high in the sky, while the second creates a remarkably effective illusion of weightlessness right here on the ground at the bottom of a massive swimming pool. Let's start with the method that sounds like something from a theme park ride, parabolic flights, famously nicknamed the Vomit Comet. This isn't a specially designed aircraft with anti-gravity generators. It's a standard plane, like a modified Boeing 707 or an Airbus, that flies in a specific roller coaster-like path through the sky. The pilot guides the plane on a steep, upward climb, accelerating at a sharp angle. Then, at the peak of the climb, the pilot reduces the thrust and the plane follows a ballistic free-fall arc back toward the Earth. This is the key moment. For about 20 to 30 seconds, everything inside the aircraft, the astronauts, their equipment, even loose pens and water droplets, is in a state of freefall. Just like the International Space Station is continuously falling around Earth, the plane and its contents are falling together through the sky. This creates a perfect brief window of microgravity. The astronauts unstrap and float through the cabin, practicing tasks like handling tools, maneuvering their bodies, and eating food, all while experiencing the real, disorienting feel of weightlessness. But there's a reason for the plane's grim nickname. As the plane pulls out of its dive and climbs again, it enters a period of high gravity or hypergravity, where everyone feels nearly twice their normal weight. This cycle of high G and zero G is repeated dozens of times per flight, and the constant, violent shifts are notoriously hard on the human body's balance system. It's an intense, physically demanding training tool, but it provides the most authentic short-term experience of weightlessness available on Earth. For training that requires hours of practice rather than fleeting seconds, astronauts turn to a different and much wetter environment, the Neutral Buoyancy Laboratory. This is not just any swimming pool, it's one of the largest indoor pools in the world, containing enough water to fill several Olympic-sized swimming pools. The principle here is not freefall but buoyancy. When an object is placed in water, it is buoyed up by a force equal to the weight of the water it displaces. By carefully adjusting the weights and flotation devices on an astronaut and their spacesuit, engineers can make them neutrally buoyant, meaning they neither sink nor float, but hover in the water column. This state is a fantastic analog for the weightlessness of space, especially for practicing the complex, choreographed movements of a spacewalk, known as an EVA or extravehicular activity. An astronaut in the pool wearing a full pressurized spacesuit that weighs hundreds of pounds on land can practice for 6-hour stretches learning how to tighten a bolt, install a new module, or repair equipment on full-scale mock-ups of the International Space Station that sit at the bottom of the pool. It's an incredibly realistic simulation of the work they will do in orbit. However, this method is not a perfect replica of space, and the differences are crucial for the astronauts to understand. The most significant factor is drag. In the perfect vacuum of space, a gentle push will send you gliding smoothly in a straight line until another force stops you. In the water, however, every movement meets resistance. Reaching out to turn a handle or move a tool is slowed by the water's viscosity. This means astronauts must learn to distinguish between the muscle memory they build in the pool and the actual force required in space. Another key difference is gravity itself. While neutral buoyancy cancels out the feeling of weight, gravity is still very much present, acting as a constant downward force. This means that in the pool, there is always a clear up and down. An astronaut can relax and let their arms float to the surface, a constant reminder of their orientation. In the true microgravity of space, that foundational sense of direction vanishes entirely. There is no up or down, only the frame of reference provided by the spacecraft. Training in both environments is essential. The parabolic flight gives them the true, disorienting physical sensation of zero-G, teaching their brain and body how to cope with the lack of orientation. The neutral buoyancy lab, on the other hand, provides the sustained, hands-on rehearsal time needed to master the intricate procedures of their mission, all while learning to work within the limitations of a bulky, pressurized suit. Together, these two training grounds on Earth provide the closest possible preparation for the extraordinary environment of space, proving that you don't need to leave the planet to learn how to live and work without the comforting, constant pull of gravity. Of all the celestial sights, few are as universally recognizable as that hazy, ethereal band of light arching across the night sky. We call it the Milky Way, a name that speaks to its soft, almost liquid appearance, like a river of spilt milk flowing through the darkness. For most of human history, that's precisely what it was thought to be: a luminous cloud, a celestial atmosphere, or a nebulous veil of light. Even with the invention of the telescope, its true nature remained frustratingly out of focus. The great astronomer Galileo himself turned his spyglass upon it and saw that the haze resolved into a countless multitude of faint stars. But the grand architecture of this starry collection was still a mystery, obscured by our own position deep within it. We were like ants trying to map the entire forest while standing on a single leaf. The myth that the Milky Way is just a featureless haze is one of perspective, a limitation we have only recently overcome with the power of modern astronomy, revealing our home galaxy to be a dynamic, structured, and breathtakingly immense island of stars. So, what are we actually seeing when we gaze at that Milky Band? We are looking edge-on into the heart of our own city of stars. The Milky Way is not a formless cloud. It is a colossal barred spiral galaxy, a vast spinning disk with a bright central bulge and majestic arms winding out from its center. That hazy band is the combined light of hundreds of billions of stars concentrated in the thin plane of this galactic disk. When we look away from the band toward the north or south galactic poles, our line of sight travels quickly out of the thin disk and into the much more sparsely populated galactic halo, so we see far fewer stars. But when we look along the plane of the disk, our gaze is directed through a staggering depth of stellar territory, like looking through the long, crowded aisle of a forest instead of across a narrow clearing. The combined glow of all those distant, unresolved suns, stars too far away for our eyes to distinguish individually, merges into that familiar, continuous river of light. The dark patches and rifts that snake through the Milky Way, like the Great Rift in the constellation Cygnus, are not empty voids. They are colossal clouds of cold, dark interstellar dust, thousands of light years across, which act like cosmic curtains, blocking the light from the billions of stars that lie behind them. For centuries, mapping the structure of this system from our vantage point inside it was astronomy's greatest cartographic challenge. The breakthrough came not from looking at visible light, which is easily absorbed by all that interstellar dust, but by observing the universe in a different part of the spectrum, infrared light. Infrared radiation has a longer wavelength than visible light, allowing it to pierce through the dusty veils that had long hidden the galactic center from our view. Pioneering missions like the Infrared Astronomical Satellite, or IRAS, and later NASA Spitzer Space Telescope began to chart the heat signatures of stars through the dust. But the mission that truly gave us our first comprehensive bird's-eye view map of the Milky Way structure was the European Space Agency's Gaia spacecraft. Gaia is not an infrared telescope, but its incredible precision has allowed it to measure the positions, distances, and motions of over 1 billion stars with unprecedented accuracy. By tracking how these stars move, astronomers can essentially run the film of the galaxy backward and forward, deducing its large-scale structure. Combining Gaia's data with infrared surveys has produced a stunningly detailed portrait of our home. We now know the Milky Way is a barred spiral about 100,000 light-years across. Its central bulge is not a sphere but a bar-shaped structure of older, redder stars, and from the ends of this bar, 2 major spiral arms, the Scutum Centaurus arm and the Perseus arm, and several minor arms spiral outward. Our own solar system occupies a rather humble, out-of-the-way neighborhood. We do not reside in one of the grand, star-forming major arms. Instead, we are located in a smaller spur of stars known as the Orion Cygnus arm, or simply the local arm, which sits between the Perseus and Sagittarius arms. Our Sun orbits the galactic center about 27,000 light-years away, completing one revolution roughly every 230 million years, a period known as a galactic year. From our suburban location, the true scale of the galaxy becomes almost incomprehensible. The Milky Way is home to an estimated 100 to 400 billion stars. Many of these stars are likely orbited by planets, meaning our galaxy could be teeming with billions of worlds. The entire system is embedded within a much larger, diffuse sphere of old stars and globular clusters called the galactic halo. And all of this is enveloped by a massive, invisible shroud of dark matter, whose gravitational pull is the only thing holding the entire spinning structure together. The hazy band we see on a clear, dark night is thus the grandest possible vista from our planet. It is the combined glow of our galactic metropolis, a silent testament to the hundreds of billions of suns that are our celestial neighbors, and a powerful reminder that our entire world, our entire solar system, is just one small, precious part of a much larger, beautifully structured, and dynamically evolving cosmic city. There's a certain magic to spotting a sudden, silent streak of light darting across the night sky, a fleeting moment of celestial beauty we've all come to call a shooting star. It's a romantic name, one that suggests a star has come loose from its heavenly moorings and is tumbling down to Earth. But the true story behind these brilliant flashes is both more humble and far more fascinating. A shooting star has nothing at all to do with stars. The real actors in this brief, luminous drama are tiny specks of cosmic dust and rock, no larger than a grain of sand or a small pebble, meeting a dramatic end in the upper reaches of our atmosphere. Understanding this spectacle means getting our terms straight, because in astronomy, the name of the object changes depending on where it is. Out in the cold, airless void of space, these small chunks of material are known as meteoroids. They are the scattered leftovers of the solar system's formation, fragments from asteroid collisions or debris shed by comets. Most are incredibly small. It's the exceptionally rare, large boulder-sized ones that ever make it to the ground. When one of these meteoroids is pulled in by Earth's gravity and slams into our atmosphere at tremendous speeds, anywhere from 25,000 to 160,000 miles per hour, the real show begins. The object is moving so fast that it violently compresses the air in front of it, creating a superheated plasma of ionized gas. This process, called ram pressure, heats the meteoroid to temperatures of thousands of degrees, causing it to glow incandescently and vaporize. This brilliant streak of light we see from the ground is what scientists call a meteor. It's not the rock itself burning, but rather the glowing, hot air surrounding it as it punches through the atmosphere. The vast majority of meteors are produced by particles the size of a grain of sand, which completely disintegrate 60 to 80 miles above the Earth's surface. But what about those rare, spectacular fireballs that outshine Venus and sometimes even fragment with a visible explosion? Those are caused by larger, perhaps fist-sized or bigger meteoroids. On the extremely rare occasion that a piece of this object is large and robust enough to survive the fiery plunge and actually reach the Earth's surface, the leftover fragment earns a new, final name, a meteorite. So, to recap the journey, it starts as a meteoroid in space, becomes a meteor as it streaks through our sky, and if it lands, it is then called a meteorite. This entire process transforms a simple piece of space debris into a momentary, brilliant beacon, a testament to the fact that our planet is constantly sweeping up material from space, adding hundreds of tons of cosmic dust to its mass every single day. Now, if you've ever gone out on a clear, dark night and seen not just one, but dozens of these streaks appearing to radiate from a single point in the sky, you've witnessed one of nature's most reliable celestial events, a meteor shower. These are not random occurrences, they are highly predictable, and their source reveals an intimate connection between meteors and the most beautiful vagabonds of the solar system, comets. As a comet travels along its elliptical orbit, it sheds an enormous amount of dust and grit, leaving behind a river of debris along its path. When Earth, in its own journey around the Sun, plows through one of these ancient cometary debris streams, our planet encounters a dense concentration of these tiny meteoroids all at once. As they enter the atmosphere in parallel paths, perspective makes them appear to radiate from a single point, much like driving through a snowfall makes the flakes appear to come from a spot directly ahead of you. This radiant point is how meteor showers get their names. The famous Perseids in August, for example, appear to stream from the constellation Perseus, while the December Geminids radiate from Gemini. Major showers like these can produce 50 to over 100 meteors per hour at their peak, each one a tiny piece of a comet, vaporizing in a final, glorious flash. The Perseids are cosmic litter from comet Swift-Tuttle, while the Geminids are curiously linked to an asteroid-like object called 320 Phaethon, suggesting a more complex origin. Every time you witness a meteor shower, you are watching the dispersed, ancient remains of a comet, a trail that may have been laid down centuries ago, intersecting with our world in a harmless, beautiful rain of light. So the next time you make a wish on a shooting star, remember the true scale of the event. You are not watching a distant sun fall from the sky. You are witnessing the final, brilliant moment of a tiny, ancient traveler, a speck of cosmic dust that has journeyed for millions of years and across billions of miles to meet its end in a spectacular blaze of light right over your head. It's a connection to the dynamic, often messy nature of our solar system, a reminder that our sky is not a static painting but a living, interactive frontier. If you could somehow bottle up a cubic meter of the space between the stars, what do you think you would find? Our instinct, reinforced by the term outer space, is to imagine a perfect, absolute vacuum, a sterile, black void completely devoid of anything at all. This image of a cosmic emptiness is one of the most persistent and understandable myths, but it's also fundamentally incorrect. The universe, it turns out, abhors a true vacuum. While the depths of space are vastly more empty than anything we can create in our best laboratories on Earth, they are far from completely blank. Instead, they are filled with a diffuse, wispy, and scientifically crucial substance known as the interstellar medium. This is the thin soup from which stars are born and into which they die, a barely their fabric woven from gas, dust, and energy that fills the vast expanses between stellar systems. Let's break down what this cosmic stuff actually is. The primary component is gas, and it's overwhelmingly composed of hydrogen, the most basic and abundant element in the cosmos. For every 1,000 atoms in this interstellar gas, about 900 are hydrogen, with most of the remainder being helium, and just a tiny sprinkling of everything else: the oxygen, carbon, iron, and silicon that make up our world. This gas exists in different states. Some of it is cold and clumpy, forming dense molecular clouds that are the nurseries for new stars. Other regions contain warm, diffuse atomic hydrogen, and still others are heated to millions of degrees by shockwaves from supernova, creating a thin, hot plasma. Mixed in with this gas are tiny solid particles we call interstellar dust. These are not like household dust. They are microscopic grains, smaller than a wavelength of light, made of carbon and silicate materials. Think of them as tiny flakes of soot and sand, forged in the atmospheres of ancient, dying stars, and then blown out into the galaxy. This dust plays a crucial role, blocking and reddening the light from distant stars, just as haze in our own atmosphere reddens the setting sun, and it also provides the surfaces upon which simple molecules like molecular hydrogen can form. Now, this isn't just a static fog. It's a dynamic environment permeated by powerful, invisible forces. Space is crackling with cosmic rays, which are not rays at all, but high-energy atomic nuclei, mostly protons racing at nearly the speed of light. These particles are accelerated by some of the most violent events in the universe, like the exploding remnants of supernova or the intense environments around black holes. They constantly bombard our planet, but our atmosphere shields us from their effects. For spacecraft and astronauts, however, they represent a significant radiation hazard, one that must be carefully considered for long-duration missions beyond Earth's protective magnetic bubble. Alongside these particles, space is also threaded with magnetic fields. These are incredibly weak compared to a simple refrigerator magnet, but because they stretch across light years, they exert a profound influence, shaping the clouds of gas and guiding the paths of those high-energy cosmic rays. To understand how this tenuous medium affects our own little corner of space, we need to consider our sun's sphere of influence, a vast region called the heliosphere. Our sun doesn't just sit motionless in a blank void. It's moving through the galaxy, and as it does so, it constantly emits the solar wind, a supersonic flow of charged particles streaming outward in all directions. This solar wind inflates a gigantic protective bubble in the interstellar medium, pushing back against the surrounding galactic gas and magnetic fields. The boundary of this bubble, known as the heliopause, is where the pressure from the solar wind finally balances the pressure from the interstellar medium. It's the ultimate shoreline where our solar system ends and true interstellar space begins. We've had a probe cross this frontier. The Voyager 1 spacecraft, launched in 1977, passed through the heliopause in 2012, becoming the first human-made object to enter the interstellar medium. The data it sent back was revolutionary. It confirmed the presence of this denser, cooler plasma outside the sun's influence, giving us our first direct taste of the galactic environment. The fact that Voyager is still communicating with us from that unimaginable distance is a testament to the fact that even empty space can conduct radio waves, allowing us to stay connected across the expanse. So why does this all matter? This seemingly empty space is the very raw material of creation. Those sparse clouds of hydrogen and dust are the cradles for new stars and planetary systems. Gravity slowly draws these wispy filaments together over millions of years, until they become dense enough to collapse under their own weight, igniting the nuclear fires of a new sun and forming planets from the swirling disk of leftover material. The dust grains within these clouds are the building blocks of more complex chemistry, potentially including the organic molecules that are the precursors to life. Furthermore, this interstellar medium is the destination for the matter expelled by dying stars. When a star like the Sun ends its life, it gently puffs its outer layers back into space, enriching the medium with heavier elements. When a massive star explodes as a supernova, it cataclysmically seeds the galaxy with iron, gold, and uranium. The interstellar medium is the galaxy's recycling system, the ecosystem that takes the ashes of dead stars and uses them to build new ones, planets, and one day, perhaps, living beings. The idea of a completely empty space is not just a minor inaccuracy. It misses the entire point of a dynamic, evolving, and deeply connected cosmos. The void between the stars is not a sterile nothingness. It is a faint, diffuse, and continuous thread of existence, the foundational substance from which everything we know, including ourselves, has emerged. It is one of the most ancient and pervasive beliefs, whispered in hospital corridors and police stations for centuries. The full moon brings out the strange in human nature. Emergency rooms staff brace for a surge in admissions, police departments prepare for a spike in erratic calls, and the very word lunatic, derived from the Latin luna for moon, embeds this idea in our language. The assumption feels almost instinctual that the same celestial force that pulls our oceans must also exert some subtle, gravitational tug on the water-based biology of our own bodies, stirring up chaos and emotion. Yet, when this deeply held belief is placed under the cold, hard light of scientific scrutiny, it evaporates like a mirage. The purported lunar effect is a powerful case study, not in cosmic influence, but in the fascinating flaws of human perception and memory. To truly dismantle this myth, we must follow the evidence, and the evidence is both vast and unequivocal. Researchers have conducted hundreds of studies over decades, analyzing colossal datasets to search for any statistical connection between the phases of the moon and human activity. They have sifted through millions of birth records, searching for a bump in deliveries during the full moon. The result, no correlation. They have meticulously examined crime statistics, emergency room admissions, and reports of psychiatric episodes. Again, no consistent pattern emerges. One of the most comprehensive analyses, published in the journal Psychological Bulletin, reviewed 37 separate studies on lunar effects and concluded that the moon accounts for no more than a random 1/100% of the monthly variation in human behavior. To put it bluntly, the moon's phases have as much influence over human activity as the flip of a coin. The scientific consensus is as solid as it gets. The moon does not make people act strangely, have babies, or commit crimes. If the data is so clear, why does the myth persist with such tenacity? The answer lies within our own minds, in a common cognitive trap known as confirmation bias. This is our brain's natural tendency to seek out, interpret, and remember information in a way that confirms our pre-existing beliefs. Imagine you are a nurse who has been told your entire career that the full moon brings chaos. On a quiet, ordinary Tuesday night, you go about your shift without a second thought. But on a busy, frantic night when the moon is full, you look out the window, see that brilliant orb, and think, aha. I knew it, it's crazy tonight because of the full moon. You have just created a mental link between two unrelated events. Crucially, you will remember that chaotic full moon night because it fits the narrative. You will forget the dozen other chaotic nights that happened during other moon phases, and you will also forget the many calm, quiet full moon nights. Your brain selectively files away the confirming evidence and discards the rest, building a convincing but entirely false case over time. This bias is reinforced by cultural storytelling. When several people in a community all share the same belief, they collectively reinforce it. A police officer mentions a weird full moon call to a colleague who nods in agreement and shares their own story. The anecdote spreads, becoming part of the unit's folklore. The news media often plays a role too. A slow news day during a full moon might feature a light-hearted story about lunar madness, further cementing the idea in the public consciousness. We are pattern-seeking creatures, and we are powerfully drawn to narratives that seem to explain the unpredictable nature of life. Blaming the moon for a random spike in emergencies provides a simple, external cause for events that are actually the result of a complex web of social, psychological, and random factors. It's a comforting, if entirely incorrect, simplification. So, what about the gravitational pull argument? It seems logical on the surface, but the physics is brutally clear. The moon's gravity does indeed cause the tides, but it does so by pulling on the entire fluid mass of Earth's oceans. The gravitational influence on a single, individual human being is astronomically minuscule, so small as to be completely biologically irrelevant. To give you a sense of scale, the gravitational pull from an obstetrician standing next to a pregnant woman in a delivery room is actually greater than the pull from the moon. Furthermore, the tidal force is a differential force. It works because there is a difference in pull between the side of Earth facing the moon and the side facing away. This difference across the diameter of our planet is what stretches the oceans. Across the tiny diameter of a human body, this difference is effectively zero. The idea that this infinitesimal force could selectively trigger labor or alter brain chemistry is a profound misunderstanding of the scales at which gravity operates. The moon's grandeur is real, but its influence over our daily lives begins and ends with the beautiful, predictable rhythm of the tides, not the unpredictable rhythm of human nature. Letting go of the lunar effect isn't a loss of mystery. It's a step toward a more accurate understanding of our own minds and our place in a cosmos governed by laws, not legends. Look up at the sky on a clear afternoon, and the sun appears as a brilliant, warm, yellow orb. Artists paint it with yellow hues, children draw it with a yellow crayon, and our entire cultural lexicon describes it as the great yellow star at the center of our solar system. It seems like the most undeniable fact of all, but what if this most fundamental observation is in fact a beautiful illusion crafted by our own planet? The scientific truth is both counterintuitive and visually stunning. The sun, in its pure, unfiltered state, is not yellow at all. It is a white star. This simple correction forces us to re-examine everything we think we know about the color of sunlight and reveals the profound influence our atmosphere has on our perception of the cosmos. To understand this, we need to journey mentally beyond the veil of our sky. Imagine you are an astronaut on a spacewalk, floating in the deep black void beside the International Space Station. If you were to look directly at the sun from that vantage point, and you would need extreme filters to do so safely, you would see a starkly different object. It would appear as a blindingly bright, pure white disk. There would be no hint of yellow, no warm golden tones. This is the sun's true color, the unaltered sum of all the visible wavelengths of light it emits. So why does this white star put on a yellow performance for us here on the surface? The answer lies in a phenomenon we encounter every single day, one that is also responsible for the blue sky above us, Rayleigh scattering. Our atmosphere is not a perfectly clear window. It's a gaseous soup of mostly nitrogen and oxygen molecules, and these tiny particles interact with sunlight in a very specific way. They are exceptionally effective at scattering the shorter wavelengths of light, the blues and violets. As sunlight streams through the atmosphere, these blue and violet waves are bounced and deflected in all directions, spreading across the entire sky. This scattered blue light is the reason the dome of the sky appears blue during the day. It's essentially a diffuse, celestial blue glow coming from every direction. Now follow the logic of what this scattering does to the sunlight that reaches your eyes directly. If the blue components are being subtracted from the direct beam and scattered away to color the sky, what is left in the beam that comes straight to you? The longer wavelengths, the greens, yellows, and reds, when these remaining wavelengths mix together, they produce the warm, yellowish-white hue that we perceive as the color of the sun. It's a constant, subtle filtering effect. The same process is amplified dramatically at sunrise and sunset. When the sun is low on the horizon, its light has to travel through a much thicker slice of atmosphere to reach you. This extended journey scatters away even more of the blue and green light, leaving behind an intense, concentrated palette of deep oranges, reds, and purples, creating those spectacular dawn and dusk skies. The sun itself can appear as a deep, fiery red orb. So, the yellow sun is not a property of the star, but a property of our planet's air. We are, in a very real sense, looking at the sun through a permanent, pale blue filter. This misconception has deeply influenced human culture and art for millennia. From the golden sun discs of ancient Egypt to the brilliant yellow halos in Renaissance paintings depicting saints and deities, we have consistently coded the sun with the color of warmth, life, and divinity. Vincent van Gogh's swirling, intense yellow suns in his paintings like The Sower are iconic expressions of this perception. Modern logos, from the smiling sun on a child's drawing to corporate branding, almost universally use yellow. This cultural anchoring is so powerful that even when science presents us with the truth, it feels instinctively wrong. Try telling a friend that the sun is actually white, and you'll likely be met with skepticism. Our lived experience, reinforced by centuries of art and language, has cemented the yellow sun in our collective consciousness. This highlights a fascinating divide between measured reality and human perception. Our instruments, like the color-calibrated cameras on space telescopes, confirm the sun's white color, but our eyes, shaped and deceived by our atmospheric home, tell us a different, equally valid story from our planetary perspective. The sun's true white color also places it perfectly within the scientific classification of stars. As we discussed earlier, a star's color is a direct indicator of its surface temperature, following the sequence O, B, A, F, G, K, M from the hottest blue stars to the coolest red ones. Our sun, with a surface temperature of about 5,500 degrees Celsius, sits squarely in the G-class category. These are officially designated as yellow dwarfs, but this is a historical classification based on their apparent color from Earth. A more accurate, physics-based description would label it a white star of the G-type. If you could line up stars by their true colors, you would see a smooth gradient from the searing blue-white of an O-type star like Zeta Ophiuchi, through the pure white of stars like Sirius, which is an A-type star, and often appears to twinkle with hints of color due to atmospheric effects, but is fundamentally white, and down to the orange of a K-type star like Arcturus and the red of an type star like Betelgeuse. Our sun fits right in the white section of this cosmic spectrum. Its light, when unfiltered, is a balanced blend of all colors, which is the very definition of white light. This is why sunlight provides such excellent neutral illumination, allowing us to see colors on Earth with such vivid accuracy. The next time you feel the warmth of the sun on your skin, remember that you are being bathed in the light of a white star. Its apparent golden hue is a gift from our own world, a gentle atmospheric lens that adds a touch of warmth to the stark, brilliant reality of the cosmos, reminding us that our perception of the universe is always and forever framed by the unique conditions of our fragile blue planet. Now, let's turn our attention from the solar myths that have shaped our understanding of home to a story that briefly set the entire world of astronomy ablaze with the possibility of something truly alien. It began with a seemingly ordinary star over 1,000 light-years away in the constellation Cygnus, known by its unromantic catalog number, KIC 8462852, but which the world would soon come to know as Tabby's star, named after the astronomer who led its study, Tabitha Boyajian. The mystery was not what we could see, but what we couldn't. thanks to data from NASA's Kepler Space Telescope, which stared unblinkingly at one patch of sky for years to find planets by the tiny dip in starlight they cause as they transit. Scientists noticed something bizarre about this particular star. Its light curve was like nothing ever seen before. Instead of the regular, gentle, periodic dips of an orbiting planet, Tabby's star displayed wild, unpredictable, and catastrophic drops in brightness. At times, its light would plummet by a staggering 22%. To put that in perspective, if a giant Jupiter-sized planet were to pass in front of it, it would cause a dip of only about 1%. These were drops so enormous they suggested something colossal was blocking the light, and the irregular, jagged shape of the dips pointed away from a simple, spherical object. In a moment of breathtaking scientific candor, the paper exploring this data listed a whole host of natural explanations, but it also included one that was, by design, extraordinary: the possibility of a vast swarm of alien megastructures, perhaps something like a Dyson sphere under construction, designed to harness the star's energy. The idea of a Dyson sphere, a hypothetical shell of solar collectors built by an advanced civilization to capture a star's entire energy output, had been a staple of science fiction for decades. To see what looked like potential evidence for one sent a shockwave of excitement through both the scientific community and the public. It was a classic what-if scenario that captured the imagination. Headlines screamed about the discovery of an alien megastructure, and for a moment it felt like we might be on the verge of the most profound discovery in human history. The star was scrutinized like no other, with radio telescopes listening intently for any signals of artificial origin and other observatories training their instruments on it, hoping to catch it in another dimming episode. Yet, amidst all the excitement, the true, grinding, meticulous work of science was just beginning. The initial alien hypothesis was a fascinating starting point, a spark of imagination. But science doesn't run on sparks, it runs on evidence, and the evidence had to be gathered. What followed was a masterclass in how science corrects itself, a slow and steady process of hypothesis and falsification. Astronomers began proposing and testing more conventional, natural explanations. The first major clue came from studying the dimming across different wavelengths of light. If a solid object like an alien megastructure made of metal and solar panels were blocking the star, it would block all wavelengths of light equally. However, when researchers analyzed the data, they found that the dimming was not uniform. The star dimmed more significantly in blue light than in red light. This is a classic signature of dust. Tiny dust grains are much better at scattering and blocking shorter, bluer wavelengths than longer, redder ones, which is also why our sunsets appear red. This finding was a massive blow to the solid megastructure idea and pointed strongly toward a circumstellar environment choked with fine, microscopic debris. The prevailing natural explanation that has since emerged is a heartbreakingly beautiful and chaotic one, far removed from the ordered geometry of an engineering project. It's believed that Tabby's star is surrounded by a vast, uneven cloud of dust and debris, likely the remnants of a catastrophic collision between planets or a family of disintegrating comets on wildly eccentric orbits. This would create a chaotic swarm of material of all different sizes, from fine dust to larger fragments, all on different paths around the star. As this irregular swarm passes in front of the star from our vantage point, it would create the bizarre, irregular, and deep dimming patterns that so baffled astronomers. The dips are not repeating with a strict period because the swarm is not a single, coherent object. It's a messy, evolving cloud, constantly changing as it orbits. Further observations confirmed this, showing that the star has also been undergoing a very long-term, gradual dimming over the past century, which also fits with a large, diffuse cloud of dust slowly drifting across our line of sight. The case of Tabby's star is now widely considered solved, not by the discovery of aliens, but by the patient accumulation of data that fit a natural, if exceptionally dramatic, model of cosmic destruction and debris. The journey of Tabby's star is not a story of failed imagination, but a triumphant story of the scientific method in action. It showcases the essential balance between open-minded creativity and rigorous skepticism. Scientists were right to consider all possibilities, no matter how fantastic, because our universe is often stranger than fiction. But they were also right to then subject that fantastic idea to the most intense scrutiny. The initial hypothesis of alien megastructures served a vital purpose. It galvanized global interest and directed a huge amount of observational power toward a truly anomalous object. This intense focus is what ultimately allowed scientists to gather the precise data needed to rule out the extraordinary claim and converge on a more likely, natural explanation. This is how science works at its best. It invites the extraordinary, but then demands the evidence. It allows for the dream of alien engineers, but then gets down to the hard work of measuring dust particles. In the end, the truth about Tabby's star is perhaps just as wondrous as the fiction. We didn't find an alien civilization, but we did discover a new class of astronomical phenomenon, a star behaving in a way we never knew was possible, giving us a front-row seat to the violent, messy, and dynamic processes that shape planetary systems. It's a powerful reminder that the universe is full of its own natural marvels, each one a puzzle waiting to be solved not by jumping to the most exciting conclusion, but by following the evidence wherever it leads, even if that path leads away from little green men and back to the humble, illuminating power of dust. Which brings us to our final and perhaps most profound myth of all, the one that has haunted humanity since we first looked up at the stars and wondered, the idea that we are completely and utterly alone in the universe. This isn't just a question, it's a feeling of cosmic isolation, the chilling thought that in all this vast black expanse, the spark of life and consciousness only flickered here on this one tiny, fragile world. Yet, when we apply the cold, hard logic of science and scale to this emotional question, the conclusion becomes almost inescapable. The universe is likely teeming with life. The contradiction between this high probability and our utter lack of evidence for it is one of the most fascinating puzzles in science, a riddle so important it has its own name, the Fermi paradox. The paradox gets its power from two simple, staggering facts. First, consider the scale. Our Milky Way galaxy alone contains an estimated 100 to 400 billion stars. For decades, we didn't know if other stars had planets, but now, thanks to missions like NASA's Kepler Space Telescope, we know they are the rule, not the exception. Nearly every star you see likely has at least one planet orbiting it. Current estimates suggest there are more planets in our galaxy than there are stars. Now, filter those planets for the ones in the Goldilocks zone, the region around a star where temperatures are just right for liquid water to exist on a planet's surface. Water is the universal solvent we know is essential for the chemistry of life as we understand it. Even if only a tiny, tiny fraction of these planets are Earth-like and in the habitable zone, the numbers are still astronomically in our favor. We're not talking about a handful of possibilities. We're talking about billions upon billions of potential incubators for life in our galaxy alone. And our galaxy is just one of an estimated 2 trillion galaxies in the observable universe. The statistical argument is overwhelming. With so many chances, it seems virtually impossible that life only started once. This is where the paradox part kicks in, famously encapsulated by the physicist Enrico Fermi during a casual lunch conversation in 1950. If life is so probable, he asked, then where is everybody? If even a single advanced civilization had arisen in the galaxy at any point in its 13 billion-year history, and if they had developed interstellar travel even at a small fraction of the speed of light, they could have colonized the entire Milky Way within a few tens of millions of years. On a cosmic timescale, that's the blink of an eye. The galaxy should be buzzing with their activity, their signals, their artifacts. Our skies should be full of their ships. And yet we see nothing, we hear nothing. We are met with a great silence. This contradiction between the high probability of extraterrestrial intelligence and the lack of any observable evidence for it is the heart of the Fermi paradox. Scientists have proposed a host of potential solutions to this puzzle, and they range from the hopeful to the terrifying. One compelling idea is the concept of the Great Filter. This theory suggests that there is some incredibly difficult step in the evolution from non-life to a spacefaring civilization that almost no species can overcome. The frightening question is, where is this filter? Is it behind us? Were we just miraculously lucky that life began at all, or that single-celled organisms made the leap to complex multicellular life? If so, we might truly be the first or one of a very few. Or, and this is the more unsettling possibility, is the Great Filter ahead of us? Is it something that inevitably dooms advanced civilizations? This could be self-annihilation through nuclear war or climate catastrophe, or perhaps a natural, cosmic disaster like gamma-ray bursts that regularly sterilize galaxies, or the emergence of a destructive technology like uncontrollable artificial intelligence that we haven't yet stumbled upon. In this scenario, the silence is ominous. It means every civilization that reaches our level of technology eventually vanishes, and we may be next, but there are less dire explanations. The cosmos is overwhelmingly vast, not just in space but in time. Civilizations could be rising and falling all the time, but their lifespans might only overlap by a few thousand years. We've only been broadcasting radio waves for about a century, a tiny, faint bubble of signal expanding at the speed of light that has so far reached only a minuscule fraction of the nearest stars. An alien civilization might have flourished and died out 100 million years ago, or they might not arise for another 100 million years. We could be like ships passing in the cosmic night, separated by chasms of time as well as space. Furthermore, their technology might be so advanced that it's unrecognizable to us. They may have moved beyond primitive radio waves to communicate using neutrinos or quantum entanglement, methods we can't yet detect. Or perhaps they are out there, but they have no interest in a noisy, primitive species like us, choosing to observe from a distance or simply ignore us entirely, the way we might ignore an anthill in a forest. This isn't just philosophical speculation, it's the driving force behind a vibrant scientific field, the search for extraterrestrial intelligence, or SETI. For decades, astronomers have been using powerful radio telescopes to scan the heavens, listening for a deliberate signal, a pattern transmission that couldn't be produced by nature. Modern SETI efforts, like the Breakthrough Listen project, use sophisticated algorithms to sift through millions of radio channels simultaneously, looking for that one in a trillion needle in a cosmic haystack. We're also searching for more subtle signs or technosignatures, such as the atmospheric pollution of an industrial civilization, city lights on the night side of an exoplanet, or the heat signature of a Dyson sphere. And the search isn't just for intelligent life. Missions to Mars are digging for fossilized microbes, and future probes are planned to explore the ice-covered oceans of moons like Europa and Enceladus, where vast subsurface seas could harbor simple, aquatic life completely separate from the story of life on Earth. Every one of these endeavors is a direct challenge to the myth of solitude, so the answer to the question, are we alone, is scientifically almost certainly no. But the Fermi paradox teaches us that the universe is not just a matter of physical scale, but of profound biological and sociological challenge. Life may be common, but intelligence, technology, and the longevity to bridge the interstellar gulfs may be exceedingly rare. The silence we hear is not an empty silence, it is a silence full of meaning, a quiet that compels us to look both outward and inward. It forces us to consider our own future, our own fragility, and the incredible responsibility that comes with being, for now, the only conscious voice we know of in the great cosmic conversation. It transforms our planet from a lonely outpost into a precious, singular cradle, a place we must cherish and protect as we continue our own first, tentative steps into the grand and silent ocean of stars. And so we reach the end of our voyage through the cosmos of misconception. We have journeyed together from the Great Wall's invisible presence to the silent, nuclear heart of the Sun. We've stood on the wind-swept plains of Mars and seen a face dissolve into a mesa, and we've peered into the profound emptiness of the asteroid belt, finding not chaos but majestic isolation. We have watched comets unveil their icy souls and seen our own atmosphere paint the moon with the light of 1,000 simultaneous sunsets. 30 myths, each one a story we thought we knew, have been gently turned over to reveal a truth that is invariably more complex, more elegant, and more wondrous than the fiction it replaces. This entire journey stands as a powerful testament to the spirit of scientific inquiry. Science is not a dry collection of facts, it is a dynamic, self-correcting conversation with the universe. It begins with a question, not an assumption. It is the courage to look at a blood moon and, instead of fearing an omen, to calculate an orbit. It is the patience to study a star's bizarre flickering and, instead of immediately declaring it aliens, to meticulously search for the signature of dust. The true power of this process is that it doesn't diminish our sense of wonder. It grounds it in reality, replacing the fantasy of exploding astronauts with the clinical reality of hypoxia doesn't make space less terrifying, it makes it knowable. Understanding that the Big Bang was an expansion of space itself, not an explosion in a void, doesn't make the origin of the universe less profound. It makes it a question that connects directly to the space between your hands as you hold them apart. Science trades the comfort of a simple story for the profound satisfaction of a true one, and in doing so, it reveals a cosmos that is far stranger, more beautiful, and more full of genuine mystery than any myth we could ever invent. This is the mindset I hope you take with you from this exploration, a critical and curious mind. Let this be an invitation to question the seemingly solid facts you encounter, whether they are about the cosmos, our planet, or the world immediately around you. Be skeptical of dramatic claims that lack evidence, and be fascinated by the slow, steady accumulation of data that leads to a deeper understanding. The next time you hear someone say that lightning never strikes the same place twice, you can smile, knowing that on a world like Jupiter, that's the only thing it does. The universe is not obligated to conform to our common sense or our cultural stories. Its truths are written in the language of mathematics, physics, and chemistry, and learning to read that language is one of the most rewarding adventures a human being can undertake. Our collective understanding of the cosmos is constantly evolving, and you are a part of that story. The conversation doesn't end here. I would love to hear from you. What was the most surprising myth we debunked today? Do you have a favorite space misconception that you used to believe, or one that you still hear people talk about all the time? Share your thoughts and your own favorite space myths in the comments below. Let's keep this cosmic conversation going. If you enjoyed this journey from fiction to fact, if you relish having your mind expanded and your perspective shifted, then please consider liking this video and subscribing to the channel. By doing so, you're not just supporting this work, you're joining a community of curious explorers, and you'll ensure you don't miss our next adventure into the wonders of the universe. Thank you for watching, and never stop looking up and questioning.